You are standing at the center of the cosmos. From this particular point, you can see in every direction. But there is a limit. A boundary not of space, but of time. The light from beyond this edge, no matter how long it travels, will never reach us. This is the story of that boundary, a line drawn by the 13.8 billion-year journey of light, and the true, staggering scale of our observable universe. What we believe we know about its size is likely an underestimation. And the truth is far grander, stranger, and more magnificent than we often imagine. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. To begin a journey into the impossibly large, we must first find our footing on the familiar. We have to start small. And for us, small is planet Earth. It feels immense, does it not? A sprawling sphere of rock and water, so vast that for most of human history, it was the universe. If you were to board a commercial airliner flying at a steady 550 miles per hour, it would take you almost 2 full days just to circumnavigate the equator. Its surface area is nearly 200 million square miles, a canvas so broad we are still discovering new things hidden within its folds. It is, from our human perspective, a world of boundless horizons. And yet, on the scale we are about to explore, it is less than a single mote of dust in a sunbeam. Let us step off our home world for a moment, and gain some perspective. Our nearest celestial companion is the moon. It hangs in our sky, a silent partner in our cosmic dance. The distance to it is, on average, about 239,000 miles. Imagine you could drive a car to the moon. Cruising at a steady 60 miles per hour, it would take you 166 days to get there. 6 months of driving, non-stop, just to reach the closest major object to us in space. In that distance, you could fit all the other planets in our solar system: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, lined up side by side, with a little room to spare. Now, let us turn our attention to the heart of our solar system, the Sun. Our star is a thermonuclear titan, a churning ball of plasma so enormous that you could fit 1.3 million Earths inside of it. It accounts for 99.86% of all the mass in the entire solar system. Everything else, every planet, moon, and asteroid, is just the leftover material. The distance from Earth to the Sun is 93 million miles. The light you feel on your face when you step outside left the Sun 8.5 minutes ago. If our airliner from before were to fly to the Sun, the journey would take 20 years. This is our home, a small, rocky world, orbiting a fairly average star, in a quiet corner of space. We have established our "you are here" marker. Now, we prepare for the first great leap. We are about to zoom out, and the comfortable scales of miles and kilometers will quickly become inadequate. The universe demands a bigger yardstick. The solar system, our cosmic neighborhood. Let us pause on the edge of our solar system and look back. From here, the Sun is just another bright star. Earth is an invisible speck. The distances are already becoming difficult to process. So, let us use an analogy. Imagine we shrink the entire solar system down. Let's take our colossal Sun and reduce it to the size of a basketball. On this scale, Earth would be a single peppercorn, orbiting about 85 feet away. Jupiter, the largest of the planets, would be a grape, orbiting at a distance of 5 city blocks. And Neptune, the most distant planet? The icy giant would be a small coffee bean, orbiting 2.5 miles away from our basketball-sized Sun. The entire realm of the planets, a system that feels so vast, would fit within the boundaries of a small city. But the solar system does not end with Neptune. Beyond its orbit lies the Kuiper Belt, a frigid disk of icy bodies, including dwarf planets like Pluto. And beyond that, enveloping the entire system like a ghostly shell, is the Oort cloud. This is a theoretical, immense sphere of trillions of dormant comets, stretching to the very edge of the Sun's gravitational influence. How far out does the Oort cloud extend? Its outer boundary could be as far as a light year away, or even further. We have sent emissaries into this void. The Voyager 1 probe, launched in 1977, is the most distant human-made object. Traveling at over 38,000 miles per hour, it finally crossed into what scientists consider interstellar space in 2012. It took 35 years. If Voyager 1 were trying to reach the nearest star system to our own, Proxima Centauri, its journey would take over 75,000 years. This is the scale of our own backyard. A system so vast that our fastest machines take decades just to leave it. And this entire system, from the blazing sun to the frozen comets of the Oort cloud, is a single, solitary point of light in the galactic sea. To go further, we need a new way to measure distance. The light year, the universe's yardstick. When we look up at the night sky, we are not just looking across space, we are looking back in time. This is perhaps one of the most fundamental concepts in astronomy, and it is the key to understanding the true scale of the cosmos. The reason is simple. Light, for all its speed, is not instantaneous. In the vacuum of space, a photon of light travels at a constant speed of approximately 186,282 miles per second. That is fast enough to circle the Earth 7.5 times in a single second. But space is so profoundly empty, and the distances are so vast, that even this speed becomes a crawl. Because of this finite speed, astronomers needed a unit of measurement that could handle the scale. This is the light year. It is not a unit of time, but a unit of distance. Specifically, it is the distance that a beam of light travels in one single Earth year. The grand total comes out to just under 6 trillion miles. 5.88 trillion miles, to be more precise. One single light year is an almost incomprehensible distance. Our closest stellar neighbor, Proxima Centauri, is about 4.24 light years away. This means the light we see from that star tonight began its journey 4.24 years ago. We are seeing it not as it is today, but as it was. When we look at Polaris, the North Star, we are seeing 433-year-old light. That light left its star around the time Shakespeare was writing his plays. Every telescope, in this sense, is a time machine. The farther away we look, the deeper into the past we peer. And this yardstick, the light year, is what will allow us to take the next step on our journey. We are leaving the confines of our solar system and venturing out into the galaxy. Journey to the stars, the Milky Way. Our sun, our solar system, our sense of home, it is just one of many. We live in a stellar metropolis, a swirling island of stars called the Milky Way galaxy. Its scale will dwarf everything we have discussed so far. The Milky Way is a barred spiral galaxy. From a distance, it would look like a magnificent, glowing pinwheel. It has a bright central bar, crowded with old, yellow stars, from which several spiral arms sweep outwards, filled with younger, blue stars, pink nebulae, and dark lanes of interstellar dust. Our sun is not in the bustling core. We reside in a smaller, partial arm called the Orion Spur, about 2/3 of the way out from the galactic center. From our vantage point, this is why we see a hazy band of light across a clear night sky. It is the combined glow of billions of distant stars in the plane of our galaxy. We are looking at the city edge on, from within. How big is our city of stars? The main disk of the Milky Way is about 100,000 light-years across. 100,000 years for light to travel from one edge to the other. Within this structure, there are an estimated 100 to 400 billion stars. Let that number settle for a moment. For every person who has ever lived, there are dozens of stars in our galaxy alone. We are now discovering that most of these stars likely have planets. Our galaxy could be home to trillions of worlds. And it is not static. Everything is in motion. Our solar system orbits the galactic center, a supermassive black hole named Sagittarius A*, at a speed of about 515,000 miles per hour. Even at this velocity, it takes us about 230 million years to complete one single orbit. The last time Earth was in this position in its galactic journey, dinosaurs were just beginning to appear. 100,000 light-years wide. Hundreds of billions of stars. A journey of 250 million years to make one lap. The scale is immense. And it is just one galaxy of many. Beyond the Milky Way, the local group and superclusters. For a long time, we thought the Milky Way was the entire universe. Other faint, fuzzy patches in the sky were thought to be spiral nebulae within our own galaxy. It was not until 1924, when Edwin Hubble used the powerful Hooker telescope, that the profound truth was revealed. He was observing the Andromeda Nebula. By identifying a special type of pulsating star within it, he could calculate its distance. The result was shocking. Andromeda was not inside our galaxy. It was nearly 1 million light-years away at the time of his measurement, a separate, vast island of stars in its own right. In that moment, the known universe expanded by an unimaginable factor. Today, we know the Andromeda Galaxy is our closest major galactic neighbor, about 2.5 million light-years away. The light hitting our eyes from it tonight began its journey before modern humans existed. When that light left, our distant ancestors, Homo habilis, were chipping away at the first stone tools on the plains of Africa. Andromeda is slightly larger than the Milky Way, and it is headed right for us, drawn together by gravity. In about 4.5 billion years, they will begin a long, slow-motion merger, a cosmic dance that will eventually form a new, giant elliptical galaxy that some astronomers have playfully nicknamed Milkomeda. But the Milky Way and Andromeda are not alone. They are the two largest members of a small galactic neighborhood known as the Local Group. This is a collection of over 80 galaxies, most of them small, dwarf galaxies, all gravitationally bound together, spanning a region about 10 million light-years in diameter. Our journey of zooming out is far from over. Our local group is an outlying member of an even grander structure, the Virgo supercluster. This is a massive collection of galaxy groups and clusters, home to over 100,000 galaxies and spanning 110 million light-years. Every point of light within this structure is a galaxy, each containing billions of stars. We are a suburb, in a neighborhood, in a cosmic metropolis of staggering proportions. And even this metropolis is just a single thread in a tapestry that defies comprehension. The cosmic web, the grandest structure. As astronomers mapped the positions of galaxies over decades, a strange and beautiful pattern began to emerge. The universe was not a random scattering of galaxies. On the largest scales, it has a structure. An intricate, sponge-like formation known as the cosmic web. Imagine zooming out so far that entire superclusters are just shimmering motes of light. From this perspective, you would see the universe organized into vast, interconnected filaments of galaxies, stretching for hundreds of millions of light-years. Where these filaments intersect, you find the most massive galaxy clusters. Between these brilliant filaments lie the great cosmic voids. These are immense, almost empty bubbles of space, sparsely populated with a few lonely galaxies. Our own Milky Way resides within a larger structure called the Laniakea supercluster, a name from Hawaiian for immeasurable heaven. This structure, containing our home supercluster and about 100,000 other galaxies, is one of those filaments in the cosmic web. It is 520 million light-years across. This cosmic web is the backbone of the universe. It is the largest structure we know of. And everything we have described so far, Earth, the Solar System, the Milky Way, and Laniakea, is just a tiny, localized piece of this web. We have journeyed from the familiar scale of our planet to the almost unfathomable. And now, we are ready to confront the central question. The fundamental misconception. The age versus size problem. We have arrived at a critical juncture, a point where a simple, logical assumption leads to an incorrect answer. This is the mystery that unlocks the true scale of the cosmos. Here is the puzzle. We have very good measurements that tell us the universe is 13.8 billion years old. We also know that the speed of light is the ultimate speed limit. Nothing can travel through space faster than light. So, the logic seems straightforward. If the universe is 13.8 billion years old, then the farthest light could have traveled to reach us is 13.8 billion light years. This would imply the observable universe is a sphere with a radius of 13.8 billion light years, making its diameter 27.6 billion light years. It makes perfect sense. It is simple, elegant, and not what we find. The actual observable universe is far larger. The most distant objects we can see are not 13.8 billion light years away from us right now. They are much further, and the total diameter is not 27.6 billion light years. It is a staggering 93 billion light years. How is this possible? How can we see the light from something that is now 46.5 billion light years away, if that light has only been traveling for 13.8 billion years? The solution is not found in the motion of light, but in the nature of space itself. The very fabric of space has been stretching. This is the concept of cosmic expansion, and it changes everything. The solution: the expanding universe. In the late 1920s, Edwin Hubble made his second revolutionary discovery. Not only were those spiral nebulae other galaxies, but almost all of them were moving away from us. And the farther away a galaxy was, the faster it appeared to be receding. What Hubble had discovered was the expansion of space itself. The best analogy is to imagine the universe as the surface of a balloon with dots drawn on it. Each dot is a galaxy. As you inflate the balloon, every dot moves away from every other dot. There is no center to the expansion on the surface. Every dot sees the exact same thing. This is what we see in our universe. This is the crucial point. The galaxies are not flying through space away from each other. The space between the galaxies is expanding, carrying them along for the ride. This stretching of space-time has a profound effect on the light that travels through it. As a photon journeys across billions of years, its wavelength gets stretched out. This is called cosmological redshift. The redder a galaxy appears, the faster it is moving away from us, and the farther away it is. And here is the solution to our paradox. Because it is space itself that is expanding, there is no speed limit on the expansion. General relativity places a limit on objects moving within spacetime, but not on the expansion of spacetime itself. Beyond a certain distance, space is expanding so fast that galaxies are receding from us faster than the speed of light. Their light, emitted today, will never reach Earth. So how can we see them at all? Because the light we see from them tonight did not leave today. It left billions of years ago, when the universe was much smaller, and that galaxy was much, much closer to us. The cosmic horizon, the edge of time. Now we can understand the true nature of the boundary of our observable universe. It is not a physical wall or an edge to space. It is a horizon of time, called the particle horizon. Let us go back to an ancient photon of light, emitted from a distant galaxy shortly after the Big Bang. When it began its journey, the universe was far smaller. The location that would one day become the Milky Way was much closer to the galaxy that emitted the photon. As the photon set off on its journey towards us, the space it was traveling through began to expand. It was like a runner on a treadmill that is getting longer. For 13.8 billion years, this photon has been traveling towards us at the speed of light. And for 13.8 billion years, the universe has been expanding, stretching the distance that photon had to cross. The particle horizon represents the absolute farthest distance from which light, emitted at the very beginning of the universe, could have possibly traveled to reach us today. It is the boundary between the events in the universe's past that we have had time to see, and the events that are still too far away for their light to have reached us. This horizon is also what makes us the center of our observable universe. Every observer in the cosmos has their own particle horizon, their own sphere of observability, centered on them. An observer in a distant galaxy would see a slightly different sphere, including regions we cannot see, and excluding regions we can. This is the ultimate horizon, defined not by a lack of things to see, but by a lack of time for their light to have gotten here. The numbers. How big is it really? So let us return to the numbers. How does this stretching of space translate into the final figure? The age of the universe is about 13.8 billion years. The light from the most distant object we can possibly see has been traveling for almost that entire time. Let us call the place that emitted this ancient light, point X. When the light left point X, calculations based on our best models of cosmic expansion suggest that it was only about 42 million light-years away from the matter that would eventually become us. That is a relatively neighborly distance. But in the 13.8 billion years that the light from point X has been traveling towards us, the space between our location and point X has been expanding dramatically. So, where is point X now? Factoring in 13.8 billion years of cosmic expansion, that location is now an incredible 46.5 billion light-years away from us. This is the radius of our observable universe, 46.5 billion light-years. This means we can, in principle, see objects in any direction out to this distance, giving our observable universe a total diameter of 93 billion light-years. 93 billion light-years. Our galaxy, the Milky Way, at 100,000 light-years across, is a tiny speck in this sphere. You could line up almost a million Milky Way galaxies end-to-end to span this diameter. This volume contains all the cosmic web, all the superclusters, all the voids. Current estimates suggest this sphere contains somewhere between 200 billion and 2 trillion galaxies. The number of stars in our observable universe likely exceeds the number of grains of sand on all of Earth's beaches and in all its deserts. The baby picture of the universe, the cosmic microwave background, CMB. So, what is it that we see at this ultimate boundary, at the very edge of our 93 billion light-year wide observable sphere? We do not see a wall of the first galaxies. We see something much more primordial. We see a wall of light. It is called the cosmic microwave background, or CMB. It is the baby picture of our universe. In the early moments after the Big Bang, the universe was an incredibly hot, dense, opaque fog of particles and light. Photons could not travel freely. They were constantly scattered by electrons, like headlights in thick fog. For about 380,000 years, the universe expanded and cooled. Eventually, it reached a critical temperature where protons and electrons could combine to form neutral atoms. This event is called recombination. Suddenly, with the electrons bound up, the photons were set free. The fog cleared. For the first time, light could travel unimpeded. The cosmic microwave background is that very light, released in that moment, now having traveled across 13.8 billion years of expanding space to reach our telescopes. Because space has stretched so much, this light, originally a brilliant yellow-orange glow, has been redshifted all the way down into the microwave part of the spectrum. Its temperature today is a mere 2.7 Kelvin, just a few degrees above absolute zero. When we build telescopes to look at the sky in microwave frequencies, we see this ancient light in every direction. It is the most distant and most ancient light we can possibly detect. This CMB light is the source of the photons from point X. It defines the surface of our particle horizon. When you look at a map of the CMB, You are looking at the oldest thing you will ever see. You are staring at the edge of observable time. The unobservable universe. What lies beyond? We have reached the edge. Not the edge of existence, but the edge of our vision. A sphere, 93 billion light-years in diameter. The final, most tantalizing question remains. What lies beyond the horizon? The simple and honest answer is, we do not know for sure. By definition, it is unobservable. Its light has not had enough time in the 13.8 billion-year history of the universe to reach us. However, we can make some educated guesses. One of the striking features of the cosmos is its uniformity. It looks roughly the same in all directions. This is the cosmological principle. There is no reason to believe that just at the edge of what we can see, everything suddenly stops. It seems far more likely that the cosmic web of galaxies, superclusters, and voids continues on. But how far? Theories like cosmic inflation suggest that in the first fraction of a second after the Big Bang, the universe underwent a period of mind-bogglingly rapid expansion. If inflation theory is correct, then the total universe is unthinkably vast. Our 93 billion light-year sphere would be like a single atom in the volume of the Earth. Some calculations suggest the entire universe could be infinite. This means that far beyond what we can see, there could be countless other domains, other observable universes from the perspective of other observers. We may be living in a small, illuminated bubble within a potentially infinite cosmic ocean. So, how large is the observable universe? It is a sphere centered on you, 93 billion light-years across. A volume of space so vast it contains perhaps 2 trillion galaxies. It is this large not simply because it is old, but because the very fabric of space-time has been stretching for 13.8 billion years. The light we see from its edge, the cosmic microwave background, is a baby picture of the cosmos, an echo of the Big Bang that has been traveling through expanding space for almost the entire history of time. When you look up at the night sky, you are not just seeing a collection of glittering lights. You are looking out across the greatest expanse imaginable. You are peering back through time, and you are staring towards a horizon beyond which lies the great unknown. You are standing on a small planet, orbiting an average star in the suburbs of an ordinary galaxy. But you are also at the center of your own observable universe. A bubble of light 93 billion light-years wide. And that is a truly incredible place to be. The universe is expanding faster than light and we can prove it. For most of our lives, we are told a simple fact. That nothing can travel faster than light. It is presented as a fundamental law of the universe, as certain as gravity. A final speed limit of 299,792,458 meters per second in a vacuum. And yet, there is something else happening. Right now, as you are listening, vast regions of the cosmos, entire galaxies, are moving away from us faster than this speed. This is not a guess. It is not science fiction. It is an observed and measured fact of the universe we live in. How can this be possible? How can the cosmos seem to violate its own most basic rule? The answer does not break physics. Instead, it reveals a quieter, stranger, and more profound reality than we might expect. It is a story that begins with a simple observation of distant stars, and ends with us looking out into a universe that is forever growing beyond our reach. In this video, we will explore this gentle paradox. We will travel back to the discoveries that first uncovered this strange reality, we will touch on the physics that makes it possible, and we will consider what it means for our future. A future where the night sky will one day be very, very empty. The foundation, the cosmic speed limit. Before we can understand the exception, we must first understand the rule. The rule, in this case, comes from the theory of special relativity, introduced to the world by Albert Einstein in 1905. At its center is a simple, yet world-altering idea. The speed of light in a vacuum, known as c, is constant for everyone. This may not sound profound at first, but its consequences are. It means that whether you are standing still or moving in a spaceship at 99% the speed of light, a passing beam of light will always be measured at the exact same speed. This is not how our everyday world works. If you are on a highway, a car passing you seems to be moving at only the difference in your speeds. But light is different. It always moves at its full speed, relative to you. To make this possible, our old ideas of space and time had to change. Einstein realized they were not separate things, but were woven together into a single fabric, space-time. And this fabric is flexible. For an object moving very fast, time itself slows down and space contracts. All to ensure that the speed of light remains constant for everyone. This is connected to the speed limit through Einstein's most famous equation, E=mc². This equation shows that energy and mass are deeply related. To make an object with mass move faster, you must give it energy. As that object gets closer and closer to the speed of light, its resistance to further acceleration increases. Pushing it from 99% to 99.9% the speed of light takes a vast amount of energy. Pushing it further takes even more. To reach the speed of light, an object with mass would require an infinite amount of energy. And because there is not an infinite amount of energy available, it is impossible for anything with mass to reach it. Light itself can only travel this fast because photons, the particles of light, are massless. For everything else, for people and planets and starships, c is an absolute barrier. It is not just a technological limit, it is a feature of the universe. It is the speed of cause and effect. So, the rule is established. Nothing with mass can travel through space faster than the speed of light. And here is the quiet detail that matters most. The rule applies to movement through space. It is a distinction that would take another theory to fully appreciate. Because while Einstein's first theory defined the rules for moving within the universe, his second would redefine the universe itself. The discovery, Hubble's revelation. Our story now moves to the early 20th century. At the time, our understanding of the cosmos was small. The common view was that the entire universe was just our own Milky Way galaxy. But there were soft, blurry patches of light in the sky that astronomers called spiral nebulae. What they were became the subject of a great debate. Were these nebulae simply gas clouds inside our own galaxy? Or were they, as a few thinkers proposed, island universes, other galaxies, just like ours, but at distances too great to imagine? The problem was a missing tool. There was no reliable way to measure such enormous distances. The first clue came from an astronomer named Vesto Slipher. Starting in 1912, he studied the light from these spiral nebulae. When he passed their light through a prism, he saw that the distinct lines in their spectra were shifted toward the red end. He correctly understood this as a Doppler shift. Just as the sound of an ambulance siren lowers as it moves away, the wavelength of light from a receding object stretches toward red. Slipher's redshifts meant these nebulae were rushing away from us. But without knowing their distances, the true meaning was still hidden. The key was found by an astronomer named Henrietta Swan Leavitt. While studying a type of pulsating star called a Cepheid variable, she discovered a perfect pattern. There was a direct relationship between how long it took a Cepheid to pulse and its true, absolute brightness. This was the standard candle astronomers had been searching for. If you know how bright something truly is, you can calculate its distance based on how dim it appears. The cosmic yardstick had been found. Then came Edwin Hubble. Using the most powerful telescope of his time, he pointed it at the Andromeda Nebula. In 1923, he found a Cepheid variable star within it. He measured its pulse, calculated its true brightness using Leavitt's law, and then determined its distance. The result was stunning. Andromeda was nearly 1,000,000 light-years away, far outside the Milky Way. The debate was over. The spiral nebulae were other galaxies. In an instant, the known universe grew from one galaxy to millions. Hubble continued his work. He measured the distances to many galaxies using Cepheids, and he measured their recession speeds using Slipher's redshift method. When he plotted the data, distance against velocity, a clear pattern emerged. The farther away a galaxy was, the faster it was moving away from us. A galaxy twice as far away was receding twice as fast. The universe was not static. It was expanding. This does not mean we are at the center of an explosion. A better image is to think of a loaf of raisin bread dough rising. If you pick any single raisin, all the other raisins will move away from it as the dough expands. A nearby raisin moves away slowly. A distant raisin moves away much faster. Every raisin sees the same thing. We are just one raisin in an expanding cosmic loaf. Hubble had discovered the expanding universe. It was a concept so strange that even Einstein, whose own theories had predicted it, at first did not believe it. This discovery rewrote our cosmic story. And within this expansion was a quiet secret that would lead us to our paradox. The plot twist: accelerating expansion. With Hubble's discovery, a new question emerged. What is the ultimate fate of the universe? For a long time, the answer seemed to be a question of balance. The universe is full of matter, and matter has gravity. Gravity pulls things together. So, gravity must be acting like a brake, gently slowing the expansion down over time. Cosmologists believed the future depended on how much matter the universe contained. If there was enough density, gravity would eventually win, and the universe would collapse in a big crunch. If there was not enough, the expansion would slow but continue forever, leading to a cold, quiet, big freeze. In the late 1990s, two teams of astronomers decided to measure the history of the expansion directly. They needed a standard candle much brighter than a Cepheid, one that could be seen across billions of light years. They found it in type Ia supernovae. These explosions occur when a white dwarf star in a binary system reaches a precise mass limit, resulting in a thermonuclear detonation that is incredibly and consistently bright. By finding these distant supernovae, the teams could measure their distance from their apparent faintness, and their redshift from their light. This would allow them to build a history of cosmic expansion. They expected to find that the expansion was slowing down. The only question was by how much. But the data showed something unexpected. Something that did not seem possible. The most distant supernovae were dimmer, and therefore farther away, than they should have been in any model where gravity was slowing things down. They were even farther than they would be if the universe were expanding at a constant speed. There was only one way to explain it. The expansion of the universe is not slowing down. It is speeding up. The result was so strange that both teams at first assumed it was a mistake. They checked their data, their methods, their assumptions. But every check confirmed the same result. The expansion is accelerating. If gravity is the brake, something else must be acting as a gentle accelerator, pushing spacetime apart. This strange, repulsive influence was given a name: dark energy. We still do not know what dark energy is. It seems to be a property of space itself. As space expands, more space is created, and with it, more dark energy, which in turn drives the expansion even faster. It is the dominant force in our universe, yet it remains almost a complete mystery. This discovery of an accelerating expansion put the final piece of the puzzle in place. If the expansion is getting faster and faster, then the paradox of faster-than-light travel was not just a possibility. It was an inevitability, the aha moment, the resolution. We now arrive at the quiet center of the paradox. On one hand, special relativity states that nothing can travel through space faster than light. On the other hand, observations show the universe is expanding, and Hubble's law suggests that at great enough distances, galaxies must be receding from us faster than light. The resolution is both simple and deeply strange. The key is in the phrase, through space. Special relativity governs the motion of objects moving through a static background. It prevents a starship from traveling from point A to point B faster than a beam of light. And in this way, it is still completely correct. No galaxy is firing rocket engines to travel at these speeds. The expansion of the universe is not an object moving through space. It is the expansion of space itself. This is the world of Einstein's other theory, general relativity, which treats space-time as a dynamic, physical thing that can stretch. Let's return to the image of the rising raisin bread. The raisins are galaxies, and the dough is space-time. A raisin does not move through the dough. It is still, but the dough between it and other raisins is expanding. If the loaf is large enough and rises fast enough, two raisins on opposite ends can be moving apart from each other faster than a tiny ant, representing a light beam, could crawl across the dough. The ant's speed limit through the dough is never broken, but the distance between the raisins can grow at a much greater rate. This is what happens in our universe. A distant galaxy is mostly at rest in its local patch of space. But the fabric of space-time between that galaxy and us is expanding. There is a specific boundary, known as the Hubble sphere, currently at a distance of about 13.8 billion light-years. At this distance, the expansion of space itself carries galaxies away from us at exactly the speed of light. Any galaxy beyond the Hubble sphere is, by definition, receding from us faster than light. This is not a guess, it is a direct consequence of our measurements. We can see galaxies with redshifts so high that we know they are far beyond this boundary, currently moving away from us at speeds multiple times that of light. The light we see from them today left billions of years ago, when that galaxy was much closer. During the light's long journey, the space it traveled through continued to expand, and the galaxy that sent the light has long since been carried beyond this superluminal edge. So, the cosmic speed limit is not broken. It is simply that the rule applies to local travel, not to the global stretching of the universe itself. Locally, nothing moves faster than light. But globally, the stretching of space has no such limit. The proof: observational evidence. This explanation is elegant, but science rests on evidence. And the evidence for this superluminal expansion is written in the ancient light that reaches our telescopes. The first piece of evidence is the redshift itself. It is not just a Doppler shift, like the sound of an ambulance. In an expanding universe, it is more profound. As a photon of light travels across the cosmos, the space it is moving through is stretching. This stretching of space also stretches the photon's wavelength, shifting it toward red. The longer its journey, the more space has expanded, and the more its light has been stretched. When we measure very high redshifts from the most distant galaxies, we are directly observing the consequence of this immense stretching. The numbers show recession velocities that are multiples of the speed of light. The second piece of evidence is the cosmic microwave background, or CMB. This is the oldest light in the universe, a faint glow left over from a time just 380,000 years after the Big Bang, when the universe first became transparent. It is a snapshot of the infant universe. Today, the points in space that emitted the CMB light we see are now, after 13.8 billion years of expansion, about 46 billion light-years away from us. The math is clear. These regions are now receding from us at speeds multiple times the speed of light. We are literally seeing the afterglow from a surface that is moving away from us superluminally. Finally, our entire model of cosmology, called the lambda-CDM model, depends on this framework. This model, which includes dark energy and dark matter, makes precise predictions about the large-scale structure of the universe, the way galaxies are arranged in great filaments and voids. The structures we see in computer simulations based on this model look remarkably like the real structures we observe in the sky. This incredible match gives us confidence that our understanding is correct. And superluminal expansion is not an optional feature of this model. It is a core and unavoidable consequence. The grand finale, the implications. So, the universe is expanding faster than light, and this does not break any laws. What does it mean for us? The implications are quiet, humbling, and a little bit melancholic. First, we must distinguish between the observable universe and the entire universe. The observable universe is a sphere around us with a boundary about 46 billion light-years away, defined by the farthest distance from which light has had time to reach us. There is no reason to think the universe ends there. It is likely vastly, perhaps infinitely, larger. This leads to another, more subtle boundary, the cosmic event horizon. This is a point of no return, currently about 17 billion light-years away. Because the expansion is accelerating, any galaxy beyond this horizon is lost to us forever. Light that it emits right now will never reach us, because the space between us and it will expand faster than the light can travel. It is like trying to swim against a current that is steadily growing stronger. Eventually, you are carried away. We can still see the old light from galaxies that have already crossed this horizon, but we will never see their present. The vast majority of the individual galaxies we can see in our sky are already unreachable. We are watching their pasts, but their futures are causally disconnected from ours. If we look far into the future, the picture becomes very still. In hundreds of billions of years, every galaxy outside of our own gravitationally bound local group will have been carried beyond our event horizon. Their light will have redshifted into invisibility. Future astronomers would look out and see an almost perfect emptiness. They would have no evidence of other galaxies, no evidence of cosmic expansion, no evidence of the Big Bang. The defining features of our universe will have been stretched away. They would be alone, unaware of the magnificent, sprawling cosmos they had lost. This is the final consequence of superluminal expansion. It means we live in a special, fleeting era. A time when we are privileged enough to see the evidence of our origins and the true scale of the universe. It is a temporary privilege. The universe is not just expanding, it is slowly pulling away from us, erasing its own history from view. The true universe is forever beyond our grasp, and even the part we can see is gently slipping away. We have traveled from a familiar law of physics to a quiet paradox, and to an elegant, if strange, resolution. We have seen that the speed of light remains the limit for any journey through space. But space itself, the fabric of reality, is not bound by that rule. It is expanding, and in the great darkness between galaxies, it is stretching faster than light. This is not a mistake in our theories, but one of the deepest predictions of our understanding of the cosmos. It reveals a universe far stranger than we might have imagined, one that is slowly closing its doors, locking away its distant regions in an accelerating silence. If this kind of quiet journey into the cosmos helps you see the world differently, consider subscribing to the channel for more explorations into the unknown. And now, I am curious to hear from you. What idea about the universe makes you feel the most small, or the most connected? I would be interested to read your thoughts in the comments below. Why the universe is bigger than it should be. There is a quiet contradiction at the heart of our understanding of the cosmos. A puzzle so simple it feels like a mistake. We know, with a gentle certainty, that our universe is about 13.8 billion years old. We also know that nothing can travel faster than the speed of light. It seems logical, then, that the absolute furthest we should be able to see is 13.8 billion light-years in any direction. The light from an object at that distance would have needed the entire age of the universe to reach us. That makes sense. It is simple, intuitive, and almost completely wrong. The reality is that the edge of our observable universe isn't 13.8 billion light-years away. It's a quiet, staggering 46.5 billion light-years away. This means the bubble of reality we can see is about 93 billion light-years across. How is this possible? How can a universe that is 13.8 billion years old be so much wider? It seems to break the most fundamental speed limit in physics. But it does not. This is not a mistake in our calculations. This quiet discrepancy is the key. It is the clue that reveals the most humbling and magnificent truth about our cosmos. The very fabric of space itself is expanding. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Imagine you are an astronomer. You point a powerful telescope, like the James Webb Space Telescope, at a tiny, empty-looking patch of the night sky. After a long time, a faint, reddish smudge appears on your screen. Analysis shows it's a galaxy. Not long ago, a galaxy named CEERS 93316 caused a stir. Initial calculations suggested it was so far away, its light had traveled for so long, that we were seeing it as it was just 235 million years after the Big Bang. But here is the paradox, the part that works against our intuition. Even if its light traveled for over 13 billion years, that galaxy is not 13 billion light-years away from us right now. It is much, much farther. Later, more careful measurements showed that this particular galaxy was not quite so ancient. But that initial puzzle tells an important story, not just about one galaxy, but about how science works. The first, startling measurement perfectly captures the grand, quiet deception of the cosmos. The universe is not just bigger than it looks, it's bigger than it logically seems it should be. Understanding why forces us to let go of our everyday intuition, and accept a reality where the stage itself is growing, even as the play unfolds. The intuitive trap. Age versus size. Let's begin by sitting with the problem, because it is a perfectly reasonable and logical idea to hold. We learn that a light year is the distance light travels in 1 year. Light moves at the ultimate cosmic speed limit, about 300,000 kilometers per second. Nothing with mass can reach this speed, and no information can move faster. So, if the universe began 13.8 billion years ago, it feels like an inescapable conclusion that the edge of what we can see must be 13.8 billion light-years away. Think of it like the sound from a distant bell. If you hear a bell that rang 10 seconds ago, and you know the speed of sound, you can calculate that the bell is about 3.4 kilometers away. You would not expect to find the bell 30 kilometers away. The distance seems fundamentally limited by the travel time and the speed of the signal. Applying this same logic to the cosmos, if we see light from a galaxy that has been traveling for 13.8 billion years, that galaxy must be 13.8 billion light-years away. This is what we call the asterisk light travel time distance. It is a measure of how long the light's journey was. And for a long time, this was the intuitive way people thought about cosmic distances. If you imagine a sphere with us at the center and a radius of 13.8 billion light-years, you get a diameter of 27.6 billion light-years. For a while, this felt like a plausible size for the observable universe. But this simple picture began to fade as our measurements became more precise. When we look at the very oldest light in the universe, the cosmic microwave background, we are seeing the faint afterglow of the Big Bang itself. This light was sent out about 380,000 years after the Big Bang, so it has been traveling for almost the entire 13.8 billion year history of the cosmos. By our simple logic, the source of that light should be 13.8 billion light-years away. And yet, when we use the tools of modern cosmology to calculate where the matter that emitted that ancient light is today, we find a number that seems impossible: 46.5 billion light-years. How did it get there? Did it travel faster than light? No. The solution to this paradox is that our simple analogy of a signal traveling through a static, unchanging space is incomplete. We have been calculating the length of the journey, but we have not accounted for the fact that the road itself has been stretching the entire time. The universe has a quiet secret, and it is called cosmic expansion. It is not that things are moving through space faster than light, it is that space itself is carrying them away from each other. The expanding universe, a stretching canvas. To understand how the universe can be bigger than its age in light years, we have to gently update our mental model. The Big Bang was not an explosion in space, like a firework in a vast, pre-existing void. The Big Bang was an explosion of space. It happened everywhere, all at once. At that first moment, all the space, energy, and matter in our entire observable universe was compressed into an unimaginably hot, dense state. And ever since then, space itself has been expanding. The classic analogy, and it's a good one, is a loaf of raisin bread dough rising in an oven. Imagine the raisins are galaxies, and the dough is the fabric of spacetime. As the dough expands, every raisin moves away from every other raisin. A raisin near the center sees all other raisins moving away from it. A raisin near the edge sees the exact same thing. From the perspective of any single raisin, it seems to be at the center of the expansion. Crucially, the raisins are not moving through the dough. They are being carried along by the dough as it expands. A raisin does not have small legs running across the dough's surface. It is still within its local patch of dough, but the distance between its patch and another raisin's patch is growing. This is the fundamental idea that resolves our paradox. Galaxies, for the most part, are not rocketing through space on their own. They are being carried apart by the expansion of spacetime itself. This has a profound consequence, one predicted by Einstein's theory of general relativity. There is no speed limit on the expansion of space itself. The rule that nothing can travel faster than light applies to motion through space. But the expansion of space is a different phenomenon. Two galaxies can be receding from each other at a speed greater than light if they are far enough apart. This does not mean they are breaking a physical law. It just means that the amount of new space being created between them every second adds up to a recession speed faster than light can travel across that same distance. This is why, when we look at the most distant galaxies, we see them redshifted. As light travels through expanding space, its wavelength gets stretched along with the space it is moving through. A light wave that was emitted as blue light in a distant galaxy will have its wavelength stretched over its billion-year journey, arriving at our telescopes as red light, or even infrared. This redshift is our primary tool for measuring how much the universe has expanded since the light was emitted, and therefore, how far away an object truly is. It is the universe's own quiet odometer, recording the stretching of spacetime. The photon's quiet journey. Let's trace the journey of a single photon, a particle of light, from the edge of the observable universe to our eye. This might help make the abstract idea of expansion feel more concrete. Our photon is born in a young, distant galaxy. When our photon is emitted, let's say 13.5 billion years ago, the universe is an infant, only a few 100 million years old. At that moment, its home galaxy is actually not that far from the clump of matter that will one day become our own Milky Way. The universe was a much smaller, denser place. Our photon begins its journey at the speed of light, the fastest anything can go. In a static universe, its path would be simple. It would travel in a straight line for 13.5 billion years and cover 13.5 billion light years. But our universe is not static. As our photon travels, the very space it is traveling through is stretching. Think of it like an ant walking on a rubber band that is being pulled apart. The ant walks at its top speed, but the finish line is constantly moving away from it because the rubber band itself is getting longer. This is what happens to our photon. For every light year it travels, space ahead of it expands. In the early universe, this expansion was happening at an incredible rate. So, while the photon moves steadfastly toward us at the speed of light, its destination, our galaxy, is being carried away from it by the quiet tide of expanding space. For billions of years, this continues. The photon travels and space expands. The expansion stretches the photon's own wavelength, shifting it further and further toward the red end of the spectrum. This is its cosmic scar, the evidence of its long journey. Then, something strange happens. About 5 to 6 billion years ago, the expansion of the universe begins to accelerate. For the first several billion years, the expansion was actually slowing down due to gravity. But then, a mysterious force, which we have named dark energy began to dominate. This force acts as a kind of anti-gravity, pushing space-time apart at an ever-increasing rate. Now, the road is not just stretching under our photons' feet. The rate of stretching is getting faster. Finally, after a journey of 13.5 billion years, our weary, redshifted photon completes its epic voyage. It enters a telescope mirror and is recorded. We look at that data and say, this light has been traveling for 13.5 billion years. That part is true, but the galaxy that emitted it is no longer just a few billion light-years away. Over those 13.5 billion years, the continuous, accelerating expansion of space has carried that galaxy to its current position, a mind-boggling distance away. The photon's journey time tells us the age of the image we see, but it dramatically understates the true, present-day distance to the object. A new vocabulary for cosmic distances. To truly grasp the scale of the universe, we need to set aside our simple definition of distance and adopt a quieter, more nuanced vocabulary. Cosmologists use several different types of distance, each describing a different aspect of an object's relationship to us. Understanding these is the key to resolving the paradox. **1. Light travel distance, or look-back time, **. This is the most intuitive and, as we have seen, the most misleading measure. It is simply the time it took for the light to reach us, multiplied by the speed of light. When we say a galaxy is 13.5 billion light-years away, in headlines, we are almost always talking about its light travel distance. This tells us how old the light is. It is a measure of time, not true space. It's like saying a letter from a distant past, which took a month to arrive, was written from a location only a month's walk away. It ignores where the sender might be by the time the letter is finally read. **2. Comoving distance. The true distance. This is perhaps the most important idea for understanding the universe's true scale. The comoving distance is the distance to an object right now, at this moment, with the effect of expansion, frozen. Think of a grid laid over the universe. As the universe expands, the grid itself expands, but the coordinates of the galaxies on that grid remain the same. The comoving distance is the distance between 2 points on that grid, scaled up to today. For a very distant object whose light traveled 13.5 billion years to reach us, its comoving distance its actual location in space today might be 35 billion light-years. This accounts for all the stretching of space that has occurred during the photon's journey. When we say the observable universe has a radius of 46.5 billion light-years, we are speaking of its comoving radius. This is the present-day distance to the most distant matter from which light has had time to reach us. **3. Angular diameter distance. The perceptual trick. This one is perhaps the most counterintuitive. You would expect that the farther away an object is, the smaller it should appear. This is true for nearby things. But in an expanding universe, this logic breaks down. For very distant objects, a strange thing happens. A galaxy that emitted its light when the universe was much smaller and it was much closer to us will appear larger in the sky than a slightly nearer galaxy that emitted its light later. Why? Because when the light was emitted, the object was physically closer to our location. That light then traveled through expanding space, preserving that apparent angular size. It is like looking at a photograph of a person taken when they were standing right in front of the camera, but then viewing that photograph from across a large room. The person in the photo still appears large, even though the photo itself is now far away. Because of this, all galaxies beyond a certain distance actually start to look bigger in the sky the farther away they are. ****4. Luminosity distance. The fading light. This measure relates an object's true brightness to how bright it appears to us. In our experience, the farther away a light bulb is, the dimmer it looks. In cosmology, there are two extra effects that make distant objects appear much, much fainter. First, the photon's energy is reduced by redshift. A blue photon gets stretched into a low-energy red photon. Second, because of accelerating expansion, the rate at which photons arrive is slowed down. If a galaxy emits 1 photon per second, we will receive them at a rate of less than 1 per second. These effects combined mean that distant objects are incredibly faint. Their luminosity distance is enormous, which is why we need incredibly powerful telescopes to see them at all. A case study in cosmic measurement. Let's return to the story of CEERS 93316. Initial reports suggested an extreme redshift, placing it in an era just 235 million years after the Big Bang. Later, more precise analysis gave it a more modest, though still very distant, redshift. This revision tells an important story, not just about one galaxy, but about how our understanding grows. Early paleontologists, for example, did not fail by getting hallucigenia wrong. They worked with incomplete evidence, revised their ideas as new data appeared, and gradually converged on a better explanation. Our understanding of the cosmos works the same way. Let's use a hypothetical galaxy, like the one CEERS 93316 was first thought to be, to see how the different distances work together. Discovery. A telescope spots a faint red object. Its extreme redness suggests it is incredibly far away. Light travel distance. Analysis suggests its light has been traveling for roughly 13.6 billion years. We are seeing a snapshot of a galaxy that existed when the universe was only about 235 million years old. This is its look-back time. Comoving distance. But where is this galaxy now? At the moment the light was emitted, it was much closer. But over the 13.6 billion years the light journeyed, space has expanded, carrying the galaxy far away. Its calculated comoving distance today might be around 35 billion light-years. It took 13.6 billion years for light to cross a gap that has since stretched to 35 billion light-years. Angular diameter distance. How big does it look? Because we see it at a time when the universe was smaller, its apparent size is larger than you would expect for something at a comoving distance of 35 billion light-years. Its angular diameter distance is much smaller. This quiet optical illusion makes it possible for telescopes to resolve its shape at all. Luminosity distance. And why is it so faint? Its light has been redshifted, losing most of its energy. Its photons arrive at our telescope much less frequently than they were sent. Both effects make it appear incredibly dim. Its luminosity distance is therefore astronomical, far greater than its comoving distance. All four distance measures give wildly different numbers. And yet, all are correct. All describe a different, valid aspect of this galaxy's reality. The light travel time tells us its age. The comoving distance tells us its location. The angular diameter distance tells us why we can see it. And the luminosity distance tells us why it was so hard to find. The engine of expansion, dark energy and Hubble's law. What is driving this incredible expansion? For the first 8 to 9 billion years of the universe's history, the expansion was actually slowing down. The collective gravity of all the matter in the cosmos was acting as a brake. But in 1998, two teams of astronomers made a discovery that caused quiet astonishment. By observing distant exploding stars, they found that these standard candles were fainter than they should be. After ruling out every other possibility, they were left with a stunning conclusion. The expansion of the universe is not slowing down, it is accelerating. This acceleration is believed to be driven by a mysterious entity called dark energy. It makes up about 70% of the universe and acts as a repulsive force, a gentle, inherent pressure in the vacuum of space that pushes everything apart. We do not know what it is. It could be a fundamental property of spacetime itself, what Einstein once called the cosmological constant. Whatever it is, it took over as the dominant force in the cosmos about 5 to 6 billion years ago. The rate of this expansion is described by Hubble's law. The law is simple. The farther away a galaxy is, the faster it is moving away from us. The Hubble constant quantifies this relationship. Current measurements are around 70 km per second per megaparsec. A megaparsec is about 3.26 million light-years. This means that for every 3.26 million light-years you go out into space, the universe is expanding about 70 km per second faster. This constant has changed over time, but its value today, combined with our knowledge of the universe's ingredients, allows us to run the cosmic clock backward. By modeling how the expansion has evolved, slowing down at first, then speeding up, we can calculate the age of the universe. And when we do, we arrive at the same number, 13.8 billion years. The very phenomenon that makes the universe bigger than it should be, expansion, is also the tool that allows us to determine its age. A history of quiet measurement. Our understanding of the universe's age and size was not given to us. It was assembled, piece by piece, over a century of patient scientific work, with many quiet corrections along the way. In the 1920s, Edwin Hubble's observations proved that distant nebulae were in fact other galaxies, and that they were all moving away. His first estimate for the expansion rate was very high, implying a universe that was only 2 billion years old. Geologists already knew that the Earth itself was older than that, a clear contradiction. Throughout the 20th century, astronomers worked to refine this number. Walter Baade, in the 1940s, realized there were two different types of key distance measuring stars, which effectively doubled the previous distance estimates and pushed the universe's age up. The work continued for decades. The picture began to clear with space telescopes. The Hubble Space Telescope Key project in the 1990s was designed to measure the expansion rate and produced a value of around 72 km per second, MPC, finally resolving the paradox of a universe younger than its oldest stars. The true revolution came in the 21st century with precision measurements of the cosmic microwave background by satellites like WMAP and Planck. By analyzing tiny temperature fluctuations in this fossil light, cosmologists could create a standard model that describes the universe with incredible accuracy. This model gives an age of the universe of 13.787 billion years. Interestingly, a quiet tension has emerged. The expansion rate derived from the early universe, the CMB, seems to be slightly different from the value derived from the late universe, stars and supernovae. This could be a hint that there is still something missing from our model, that our understanding is not yet complete. This journey of discovery shows how science progresses. Each new piece of evidence has painted a picture of a cosmos far grander, stranger, and more magnificent than we ever imagined. So, we return to our central question. Why is the universe bigger than it should be? The answer is as profound as it is simple. Because the should be was based on a quiet, false premise. We live in a dynamic, evolving cosmos, not a static one. The 13.8 billion year age of the universe is not a radius, but a ticking clock against which an even grander process unfolds: the expansion of space itself. The light from the most distant galaxies began its journey when the universe was young and small. For billions of years, it raced toward us, while the very ground beneath it was being stretched out, creating more and more distance for it to cover. That stretching, driven first by the inertia of the Big Bang and now accelerated by dark energy, is what created the disconnect between time and distance. The 93 billion light-year observable universe is not the entire universe. It is just our bubble of visibility, the region from which light has had time to reach us. There are almost certainly galaxies beyond that horizon, but due to the accelerating expansion, the light from those galaxies is on a journey it can never win. The space between us and them is expanding faster than the light can travel through it. They are beyond our cosmic horizon, forever lost to us. Every time you look up at the night sky, you are not just seeing points of light. You are seeing ancient history, delivered by photons that have won an incredible, quiet race against the expansion of space-time. You are seeing evidence of a universe that is not just a container, but an active, growing entity. The universe isn't bigger than it should be. It's exactly as big as a universe with our laws of physics is supposed to be. And that reality is far more mind-blowing than any simple mistake. The universe is expanding faster than light, and it changes everything. There is a rule in our universe, a speed so fundamental to reality that we know it by a single letter: c. The speed of light, 300,000 kilometers per second. It is the fastest anything can travel through space. It feels absolute, a law that cannot be broken. And yet, in a quiet and profound way, the universe is moving past that limit. That gentle rule, the one piece of physics we feel we know, is being surpassed. Not by a futuristic ship in a distant galaxy, but all around us. Right now, as you watch this, enormous parts of our own universe are moving away from us faster than light can travel. This is not a theory or a mistake. It is a measured and accepted fact of the world we live in. And realizing this does not just bend a rule, it changes our entire sense of the cosmos. It asks us to accept a reality where the distance between 2 points can grow faster than a beam of light can cross it. This is the story of how that is possible. It is the story of a quiet contradiction that, once understood, changes our idea of what the universe is, and what our place within it will eventually be. This is the story of how space itself is gently pulling the universe apart, faster than light, and creating one of the deepest mysteries in all of science. A quiet inconsistency. To understand this puzzle, you first have to understand the rule it seems to break. The story begins, as many stories about the cosmos do, with Albert Einstein. In 1905, with his theory of special relativity, he described the universe's ultimate speed limit. He showed that as an object with mass moves faster and faster, its own mass appears to increase. The energy needed to push it further grows, until at the speed of light, it would become infinite. It is the universe's most fundamental boundary. Nothing with mass can reach the speed of light. For more than a century, this has been a foundation of physics. For a time, our picture of the universe was a settled one. Einstein himself first thought the universe was, on the largest scales, unchanging. But that comfortable idea was about to be gently taken apart. In the 1920s, an astronomer named Edwin Hubble, using the most powerful telescope of his time, made a series of observations that would change human perspective forever. He was measuring the light from distant smudges in the sky, then known as spiral nebulae. He confirmed they were not clouds inside our own Milky Way, but entire galaxies, island universes, millions of light years away. But he found something else. Something quiet and strange. The light from almost all of these distant galaxies was stretched, shifted toward the red end of the spectrum. This is called redshift, and it is a cosmic version of the Doppler effect. It's the same reason a siren sounds lower in pitch as it moves away from you. A redshift in starlight meant the galaxies were moving away from us. And then came the most important part. Hubble discovered a clear relationship. The farther away a galaxy was, the faster it seemed to be moving away. This was the first real evidence that our universe was not static. It was growing. Now, let's pause here and follow this idea. We have now measured, with incredible care, that this expanding universe began in a Big Bang about 13.8 billion years ago. We also know that the speed of light is the universe's speed limit. So, if you imagine light from the farthest away object starting its journey toward us at the very beginning, it should have been traveling for, at most, 13.8 billion years. This leads to a simple-sounding question. How far away should the edge of our observable universe be? The answer feels obvious. If light has traveled for 13.8 billion years, then the most distant things we can see should be 13.8 billion light-years away. Our observable universe, the sphere of everything whose light has had time to reach us, should be twice that, or about 27.6 billion light-years across. It makes perfect, intuitive sense. And yet, when we measure the universe, it tells us a different story. When astronomers measure the actual size of the observable universe, they find a very different number. The sphere of everything we can see is not 27.6 billion light-years across. It is approximately 93 billion light-years across. The edge of what we can see, the cosmic horizon, is not 13.8 billion light-years away. It is about 46.5 billion light-years away, in every direction we look. Let that settle for a moment. The light from the most distant galaxies has traveled for nearly 13.8 billion years to reach us. Yet the things that sent that light are now, today, 46.5 billion light-years from where we are. How is this possible? How can a journey of 13.8 billion years bring us light from something that is now so much farther away? It is a riddle that seems to go against simple math, a quiet clue that something else is going on. It's like a runner finishing a marathon, only to find the starting line is now 3 times farther away than the distance they actually ran. Something else has been happening. Something that changes the racetrack itself. The fabric of space. The answer to this quiet riddle is one of the most elegant concepts in all of science. To understand it, we have to stop thinking of the universe as an empty room that things move around in. We have to start thinking of space itself as a thing. A fabric. Something that can stretch. The most familiar analogy for this is a loaf of raisin bread dough rising in an oven. Imagine the galaxies are raisins, and space is the dough. As the bread bakes, the dough expands everywhere at once. From the perspective of any one raisin, all the other raisins seem to be moving away. A nearby raisin might only move a little. But a raisin on the far side of the loaf, carried by all the dough in between that is also expanding, will move away by much more. The raisins are not moving through the dough. They are being carried apart because the dough itself, the space between them, is expanding. This is the key. Einstein's speed limit remains completely true. No ship can fire its engines and travel through space faster than light. The raisins cannot pop out and fly through the bread. The law applies to motion within the fabric of space-time. But the expansion of the universe is not motion through space. It is the expansion of space. And there is no known speed limit for the expansion of space itself. The cosmic ruler is simply getting longer, and the galaxies are being carried along with it. This is what Edwin Hubble's discovery described. His observation, now known as Hubble's law, can be expressed as a simple relationship. V equals h0d. A galaxy's apparent speed, v, is equal to its distance from us, d, multiplied by a number called the Hubble constant, h0. Current measurements from telescopes like James Webb and Hubble suggest this number is around 73 km per second per megaparsec. A megaparsec is just a unit for a very large distance, about 3.26 million light-years. So what does that number mean? It means that for every 3.26 million light-years farther away you look, the expansion of space carries a galaxy away from us 73 kilometers per second faster. Think about what that implies. For a galaxy that is 1 megaparsec away, the expansion speed is a gentle 73 kilometers per second. For a galaxy 100 megaparsecs away, that speed is 7,300 kilometers per second. Now, just keep going. Because the speed adds up with distance, there must be a point where the total speed of recession becomes enormous. And eventually, at a distance of about 14.4 billion light-years, a boundary known as the Hubble radius, the combined speed of all that expanding space surpasses 300,000 kilometers per second. It surpasses the speed of light. Every galaxy beyond that distance is, right now, receding from us faster than light. Not because it is moving, but because the enormous volume of space between us and it is stretching so quickly that it carries the galaxy away at that speed. This is not a fringe idea. It is a direct result of living in an expanding universe. Now, we can finally solve the puzzle of the light that is 46.5 billion light-years away. Think about one of those distant galaxies we see. When the light we see today first left that galaxy, nearly 13.8 billion years ago, the galaxy was not 46.5 billion light-years away. It was much closer. But in the 13.8 billion years its light has been traveling toward us, like a messenger on a cosmic journey, the space between us and that galaxy has been continuously stretching. Every year of the photon's journey, the distance it still had to cover grew, because the path itself was getting longer. So, while the photon traveled steadily at the speed of light for 13.8 billion years, the galaxy that sent it was carried away by the current of expanding space. It was swept from its original, closer position, all the way out to its current, mind-boggling distance. We are seeing a 13.8 billion-year-old image from the past of an object whose present reality is almost impossibly far away. The law is not broken. The universe is just far stranger, and far larger than our intuition could prepare us for. The cosmic horizon. Understanding that space itself can expand faster than light is a profound shift in perspective. But the story does not end there. In 1998, two teams of astronomers made a discovery that added another, even quieter and more startling, layer to the story. A discovery that would earn a Nobel Prize. They were looking at distant supernovae, exploding stars that serve as standard candles, objects of known brightness that help us measure cosmic distances. They expected to find that the expansion of the universe was slowing down. After all, the gravity from all the matter in the universe should be gently pulling everything back together. They found the exact opposite. The distant supernovae were even dimmer, and therefore even farther away, than they should have been. This meant that in the last few billion years, the expansion has not been slowing. It has been speeding up. It is accelerating. The cause is a mysterious presence we call dark energy. It seems to be a property of space itself, an inherent energy in the vacuum that acts like a gentle, persistent push, forcing space-time apart. We do not know what it is, but we can see its effects. Today, it seems to make up about 70% of everything in the universe. This accelerating expansion has a profound and somewhat lonely consequence. It creates a boundary in our universe, a true point of no return. It is called the cosmic event horizon. It is a frontier beyond which we will forever be disconnected. Think of it this way. Imagine a galaxy that is already being carried away from us faster than light. Because the expansion is accelerating, that galaxy's speed away from us will only increase. The river of space is flowing faster. Light from that galaxy, trying to swim upstream toward us, is like a boat in a current that is getting stronger. At a certain distance, the flow of space away from us becomes so fast that the light can no longer make any progress toward us at all. From that moment on, even as the light continues to travel at light speed in its local space, the expanding universe carries it backward, away from us. That galaxy has crossed the cosmic event horizon. Its light will never reach us. It has quietly slipped away from our future universe. This forces us to see a difference between the observable universe and the reachable universe. The observable universe is everything whose past light can reach us today. But the reachable universe, the galaxies we could, in theory, ever travel to, is much smaller. Current estimates place this limit at a distance of about 15 to 16 billion light-years. Any galaxy beyond that is already moving away so fast that even a ship traveling at light speed could never reach it, because the space in between would be stretching faster than the ship could cross it. They are forever beyond our physical grasp. And the situation becomes even stranger when we look to the distant future. Even if we could wait forever, we will not get to see more and more of the universe. As dark energy continues to accelerate the expansion, more galaxies will cross that event horizon and fade from our future view. There is an ultimate, future visibility limit, the farthest objects whose light, emitted today, could ever reach us, even with an infinite amount of time to wait. Current models place this limit at about 62 billion light-years. This leads to a startlingly specific thought. Even with an eternity to wait, we will only ever be able to see a fraction of the galaxies that exist. Beyond that limit lies a potentially infinite cosmos that we will never see, never interact with, and never know. We are living in a quiet bubble, and the walls of that bubble are defined not by an edge, but by the overwhelming, gentle expansion of space itself. We are being isolated. If spending some time with these quiet cosmic ideas is something that helps you feel a sense of wonder, consider subscribing. We explore these mysteries every week. And if you'd like to support how these videos are made, you can join our community on Patreon. Now, let's return to what this all means for the ultimate fate of everything. A universe of mysteries. This story of an accelerating, faster-than-light expansion might sound like a complete picture. It is not. In fact, these ideas have led us to one of the deepest puzzles in modern cosmology, a gentle disagreement known as the Hubble tension. The Hubble tension is a disagreement about one number. The exact speed of the universe's expansion today, the Hubble constant. The problem is, we have two different ways of measuring it, and they give us two different answers. The first method is the local one. Astronomers use telescopes like Hubble and James Webb to look at things relatively close to us, like certain types of stars and supernovae. By measuring how far away they are and how fast they are moving away from us, they can calculate the expansion rate right now. This method consistently gives a value of about 73 kilometers per second per megaparsec. The second method looks back to the early universe. Scientists study the faint afterglow of the Big Bang, the cosmic microwave background. This light, from when the universe was just 380,000 years old, holds a detailed map of the infant cosmos. Using our best understanding of physics, cosmologists can predict what the expansion rate should be today based on that early map. This method consistently gives a lower value, around 67 or 68. The difference between 67 and 73 may not sound like much, but the measurements are so precise that the difference is real. It is not likely a mistake. Both results seem correct, which suggests that our story of how the universe grew from its early state to today might be missing a chapter. Our understanding, as one scientist put it, may be incomplete. This tension is causing scientists to ask quiet questions about everything. Perhaps dark energy is not constant. Maybe it changes over time. Other ideas wonder about new kinds of particles in the early universe, or even that spacetime itself has a kind of resistance to being stretched. The Hubble tension is not just a problem, it's a clue. It is a quiet sign pointing toward new physics, toward a deeper understanding of reality that is waiting to be found. And all of this is happening inside our small, observable bubble. The 93 billion light-year sphere we can see is just that. What is observable to us? It is our horizon, but it is almost certainly not the edge of everything. According to the theory of cosmic inflation, our best idea for what happened in the first moment after the Big Bang, the universe grew by an unimaginable amount. If this is right, then the total universe is vastly larger than the part we can see. So large that the number becomes meaningless. For all we know, our entire observable universe is just one quiet corner in an immense cosmic reality. The universe could be finite, or it could be infinite. We may never know. We are adrift on a cosmic ocean, and the farthest shore we can see is just a limit made of light, time, and the relentless stretching of space. The fact that the universe is expanding faster than light is not a flaw in our laws of physics. It is a profound feature of our reality. It changes our picture of the cosmos from a static stage to something dynamic, evolving, and deeply strange. Einstein's speed limit, c, still holds for any object moving through space. But space itself plays by different rules. It has no speed limit. Its expansion is an engine of both creation and isolation. This expansion is what solves the quiet riddle of our oversized universe, allowing light from the dawn of time to reach us from places that are now impossibly far away. And this same expansion, driven by the mystery of dark energy, is what is slowly, gently, pulling the universe apart from our view. It has built a cosmic event horizon, a veil beyond which most galaxies are already slipping, their last light fighting a losing battle against a current of spacetime that flows ever faster. The great scientific puzzles of our time, dark energy, the Hubble tension, are all tied to this one simple fact: the universe is growing. They are clues, whispering to us that our understanding, for all its success, is not yet complete. There is new physics waiting to be discovered in the way the universe grows. This discovery changes our place in the cosmos. It tells us that we live in a finite bubble of knowing, a sphere of observation whose boundary is drawn by expansion itself. Most of reality may lie forever beyond our reach, receding into a darkness caused not by distance, but by the very creation of space between us. The universe is not just bigger than we imagine, it is growing in a way that is bigger than we can imagine. So the next time you look up at the night sky, remember what you are truly seeing. You are not just looking out into a quiet emptiness. You are looking back in time, across a dynamic, stretching fabric of reality. You are seeing ancient light from galaxies being swept away on a cosmic current, a current that is carrying almost everything away from us, faster than light, and in the end, forever. And the deepest mystery of all might be not what lies beyond that horizon, but the nature of the expanding space that created the horizon in the first place. Galaxies are disappearing from the sky forever. For nearly all of time, the night sky has appeared constant. A silent expanse of stars and distant galaxies, unchanging and eternal. Human history has measured itself against this celestial backdrop, seeing it as a symbol of permanence in a world defined by change. But this apparent permanence is an illusion, a view unique to our specific moment in cosmic history. A quiet, profound transition is underway. As we watch, entire galaxies, each a collection of countless stars and potential worlds, are moving beyond a point of no return. They are not vanishing, but are being carried away from us, their light lost to our future sky. This is not speculation. It is a consequence of the physics that governs our universe, and it means that any intelligence in this part of the cosmos is being settled into an increasingly isolated region of space. To understand how this is happening, we need to begin a journey. Not simply through space, but through the lifespan of the universe itself, from its earliest moments to its distant future. It is a story that reveals both the scale of the cosmos and the quiet isolation that awaits within it. If this kind of calm exploration into our universe is something you find valuable, consider liking the video and subscribing. And wherever you are right now, Whether in a city or somewhere quiet, feel free to share where you're watching from in the comments below. Imagine you are on a vessel in a vast, dark ocean. In every direction, the lights of other vessels are visible across the water. For a moment, there is a sense of connection to a large, populated expanse. Then, you begin to notice something about the lights on the farthest horizons. They seem to be moving away, and their speed appears to increase with distance. The lights at the very edge of vision begin to stretch, their colors shifting toward a dim red before fading from view entirely. They have not ceased to exist, they have simply moved beyond a horizon, their light no longer able to cross the expanding gulf of water. Now, imagine this is not an ocean, but the fabric of spacetime. And the vessels are not ships, but entire galaxies. This is what is happening to our universe. For most of history, the universe was seen as a static and eternal stage. The stars were considered fixed points of light, and the faint, fuzzy patches seen through early telescopes, the spiral nebulae, were thought to be clouds of gas inside our own Milky Way. Our galaxy was, for all practical purposes, the entire universe. This picture began to change in the early 20th century, through the work of an astronomer named Edwin Hubble. Using a new generation of powerful telescopes, he made a series of discoveries. By observing a type of star known as a Cepheid variable within the Andromeda Nebula, he was able to calculate its distance. The result was unexpected. Andromeda was not a cloud within our galaxy, but a separate, island universe, millions of light years away. The universe was suddenly a vast collection of innumerable other galaxies. As Hubble and his colleagues studied these distant galaxies, they found something unusual about their light. It was redshifted, or stretched to longer wavelengths. This is analogous to the Doppler effect, where the pitch of a sound changes as its source moves away. For light, moving away from an observer shifts its wavelengths toward the red end of the spectrum. Hubble discovered that nearly every galaxy he observed was redshifted. More than that, the farther away a galaxy was, the faster it appeared to be moving away from us. The implication was inescapable. The universe was not static. It was expanding. Every galaxy was moving away from every other, not through space, but because space itself was stretching. The common analogy is that of raisins in a loaf of baking bread. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single one, all others appear to be receding. This discovery reshaped cosmology. If the universe is expanding now, it must have been smaller and denser in the past. This led to the theoretical framework of the Big Bang, an explosive expansion that marked the origin of the universe approximately 13.8 billion years ago. For a long time, the ultimate fate of this expansion was thought to depend on a contest between two forces: the outward momentum from the Big Bang, and the inward pull of gravity from all the matter in the universe. If there was enough matter, gravity would eventually win, reversing the expansion in a big crunch. If there was not enough, the universe would expand forever, its expansion gradually slowing as it faded into a big freeze. For much of the 20th century, astronomers worked to measure the density of the universe to learn which path it would take. But the cosmos held a different possibility, a detail that would once again require a revision of our understanding. In the late 1990s, two separate teams of astronomers set out to measure the expansion rate with new precision. They used a specific kind of stellar explosion called a Type Ia supernova. These events are useful because they always occur at a specific mass, and therefore have the same intrinsic brightness, making them reliable, standard candles, for measuring cosmic distances. By measuring the apparent dimness of these supernovae in distant galaxies, astronomers could calculate how far away they were. By measuring their redshift, they could determine their speed. The goal was to see how the expansion rate had changed over time. The expectation was that the expansion would be slowing down. That is not what the data showed. The distant supernovae, which show the universe as it was billions of years ago, were dimmer than they should have been. The only explanation was that the expansion of the universe in the past was slower than it is today. The expansion was not slowing down. It was accelerating. It was as if an object thrown into the air, instead of slowing, began to speed up and move away faster. Some previously unknown influence was overpowering gravity on cosmic scales, pushing space apart. This influence was given a name that reflects its mysterious nature: dark energy. Later observations, including maps of the cosmic microwave background, the afterglow of the Big Bang, have confirmed this acceleration. The universe we inhabit is now understood to be composed of roughly 5% normal matter, 27% dark matter, and 68% dark energy. This invisible, repulsive energy is the dominant component of the cosmos. The simplest model for dark energy is that it is a cosmological constant, an intrinsic property of space itself. As more space comes into being through expansion, more of this energy appears with it. In the early universe, gravity was the stronger force, and the expansion was slowing. But around 6 billion years ago, after the universe had expanded enough to dilute matter's gravitational grip, dark energy became dominant, and the era of acceleration began. The precise nature of dark energy remains one of the great unsolved questions in physics. For now, however, the model of a constant dark energy driving a runaway expansion is the one best supported by evidence. And this expansion has a profound consequence. It creates a boundary in our universe, a point of no return known as the cosmic event horizon. To understand this boundary, we must first distinguish it from the edge of the observable universe. When we look into space, we are looking into the past. The universe is approximately 13.8 billion years old, so the farthest we can possibly see is light that has traveled for nearly that entire time. This boundary is known as the particle horizon. Because space itself has expanded as that light traveled, the source of that light is now about 46.5 billion light-years away from us. This defines the 93 billion light-year sphere of the cosmos that is, in principle, visible to us today. The accelerating expansion, however, creates a different kind of boundary, one based not on the past, but on the future. This is the cosmic event horizon. It is a distance beyond which the expansion of space carries galaxies away from us faster than the speed of light. This does not violate physics. The rule that nothing can travel faster than light applies to motion through space, not the expansion of space itself. Today, this cosmic event horizon is about 16 billion light-years away. Any galaxy currently beyond that distance is receding from us faster than light. The consequence is absolute. Any light emitted by a star in that galaxy right now will never reach us. The space it must cross is expanding faster than the light can travel through it. That light is on a cosmic treadmill it can never overcome. The galaxies beyond this horizon are lost to our future. What is quietly humbling is the relationship between our observable universe and this point of no return. Our observable universe has a radius of 46.5 billion light-years. The event horizon has a radius of only 16 billion light-years. This means the vast majority of the galaxies we can see in our telescopes, in fact, about 94% of them, are already beyond the event horizon. We can still see their ancient light, emitted billions of years ago when they were closer to us. But in the time that light has traveled, the accelerating expansion has carried those galaxies across the threshold. The light they emit today will never arrive. We are, in a sense, watching a recording of a universe that is already causally disconnected from ours. What does this mean for the distant future? Our Milky Way galaxy is part of the Local Group, a small cluster of galaxies bound together by gravity. In about 4.5 billion years, the Milky Way and the Andromeda galaxy will begin to merge. Over hundreds of millions of years, they will combine into a single, larger elliptical galaxy, which some have called Milky Way. Over the next 100 billion years, the other smaller galaxies in the local group will also be absorbed. Outside this gravitationally bound island, the cosmic exodus will continue. Every other galaxy and galaxy cluster will be pushed by dark energy across the event horizon, their light red shifting until it becomes undetectable. Imagine an astronomer 100 billion years from now, on a planet within the solitary Milky Way galaxy. Looking out into the cosmos, they would see nothing beyond the stars of their own galaxy. The deep blackness between the stars would be empty. The implications for knowledge are profound. All of modern cosmology is built on observing the light from distant galaxies. Their redshift tells us about expansion, and the cosmic microwave background tells us about the Big Bang. A future astronomer would have none of this evidence. They would inhabit what appears to be a single, static galaxy surrounded by an infinite void. Based on their observations, they might logically conclude that their galaxy is the entire universe. The deepest truths about the cosmos, its origin, its scale, its evolution, would be undiscoverable. The story of the universe would be lost. Over trillions of years, even the stars within the Milky Way galaxy will exhaust their fuel and die out. The universe will enter a degenerate era, populated by cooling stellar remnants. Over unimaginable timescales, even these may dissipate. The final predicted state is a heat death, a near-perfect vacuum, growing colder and more dilute for eternity, a dark and silent void. This is the destination implied by the runaway expansion we observe today. This journey can seem unsettling. It suggests a future of isolation and decay. The realization that most of the galaxies we can photograph are already unreachable can feel profound and strange. Our existence is unfolding on a small island of matter being cast away into an expanding emptiness. But there is another perspective, one of wonder and gratitude. We are living in a very specific and privileged time. We exist in the stelliferous era, the age of stars. A brief, shining moment when the cosmos is filled with light, structure, and complexity. That view of the night sky is not a symbol of permanence, but a snapshot of a dynamic and finite spectacle. Every faint galaxy is a testament to our fortune. We live at a time when we can not only see them, but also understand what they are. We can read the story of the universe written in their ancient light. Future civilizations, trapped within their island galaxy, will likely not have this privilege. The evidence will be gone. The story will be erased. This knowledge is a gift of time and chance. It reframes our place in the cosmos. We are not simply specks in a void. We are, for this moment, witnesses. We are the generation able to see the full expanse of the cosmic ocean, just before the fog of expansion hides it from view. The fact that these galaxies are disappearing makes our ability to see them now all the more precious. It gives our exploration of the cosmos a quiet urgency. The images captured by our telescopes are historical documents from a brief era when the full glory of the universe was visible. The next time you feel small under the vastness of the night sky, remember this. The view is not forever. And our fleeting moment to witness it all is a call to look up, to be curious, and to appreciate the profound, beautiful, and temporary cosmic dawn in which we are so lucky to be alive. The universe is lying about its size. There is a quiet contradiction written in the light of the oldest stars. It's a puzzle that seems to gently bend the rules of the world as we know it. We are told, with a precision that feels solid and dependable, that the universe began 13.8 billion years ago. We are also told that nothing can travel faster than the speed of light. These two ideas feel like bedrock. They are foundations for our understanding of the cosmos. And yet, when we point our instruments toward the sky and measure the space around us, we find something that doesn't quite fit. We find a universe that is 93 billion light-years from one edge to the other. It's worth taking a moment to let those numbers settle. An age of 13.8 billion years. A size of 93 billion light years. It feels like a mistake, a soft but persistent error in our cosmic accounting. It is as if we found a tree we knew to be 20 years old, but which stood 200 feet tall. It feels like a story that is not being told straight. How can a space be so much wider than the time light has had to cross it? This question has sat with scientists for a long time. But the answer is not a mistake in our measurements, nor is it a lie. It is the result of one of the most fundamental properties of our universe. The fabric of space itself is stretching. It is growing in a way that our everyday intuition is not built to understand. Grasping how this is possible does not just solve a puzzle. It quietly changes how you see everything, from the starlight in the night sky to your own place within it. Our minds are right to pause here. Every lesson, every story about science has reinforced one rule above all. The speed of light is the final speed limit. Laid down by Albert Einstein, it is a constant. Nothing with mass can reach it, and no information can move faster. If a star fades on one side of the galaxy, the other side will not know until its light completes the journey, traveling at its unyielding pace. So when we hear that the universe is 93 billion light-years across, our internal logic flags an error. If 13.8 billion years have passed, then the farthest anything could have possibly traveled from a central point is 13.8 billion light-years. The full diameter, then, should be twice that, 27.6 billion light-years. That number feels correct. It respects the rule. But it is deeply, quietly wrong. The universe we observe is more than 3 times larger than our intuition allows. This is not a small discrepancy, it's a vast gap in understanding. For a while, it seemed that either the age of the universe was wrong, or Einstein's most famous law had been broken. The truth, as it often is, turned out to be more subtle. The solution is found in a careful distinction within Einstein's own work. The cosmic speed limit applies to things moving through space. It says nothing at all about the expansion of space itself. This is the detail that matters. It is the key to understanding the story the universe is telling us. The rules of the road. To truly grasp this, we first have to become familiar with the rule it seems to bend. Einstein's theory of special relativity, from 1905, changed our understanding of space and time. At its center is a simple idea. The speed of light in a vacuum is the same for everyone, no matter how they are moving. Whether you are standing still or moving at half the speed of light, a beam of light will move away from you at the exact same speed. This has unfamiliar consequences. It means that as something with mass gets closer to the speed of light, its time slows down relative to a stationary observer, and the energy needed to push it faster grows, becoming infinite at the moment it would reach light speed. This is why nothing with mass can reach it. This is the speed limit for any journey from one point to another within spacetime. Think of it like a road. Special relativity sets the speed limit for all the cars on that road. No car can go faster. But the rule applies to the cars, not the road itself. Now, imagine the road is made of a material that can stretch, and that it is stretching everywhere at once. 2 cars could be moving, both following the speed limit relative to the pavement directly beneath them. But if the road between them is stretching fast enough, the distance separating the 2 cars could be growing. This is the profound insight of general relativity, Einstein's later theory of gravity. General relativity describes gravity not as a pull, but as the curvature of spacetime. A massive object like the Sun doesn't pull the Earth. It warps spacetime around it, and the Earth follows a straight path through that curved space, which we see as an orbit. But this theory also means spacetime itself can be dynamic. It can bend, ripple, and, for our puzzle, it can expand. When cosmologists say the universe is expanding, they don't mean galaxies are flying outward from a single point into an empty void. That is a common misunderstanding. Instead, the space between the galaxies is growing. The galaxies themselves are mostly just carried along. And here is the crucial detail. There is no speed limit on the expansion of spacetime itself. It is not an object moving through space, so the rules of special relativity do not apply. The distance between two very distant points can increase faster than the speed of light, and this does not violate any laws. This isn't a fringe idea, it is a core part of modern cosmology. The puzzle, then, is not a paradox. It is a failure of our intuition, which is built on moving through a space that feels fixed and unchanging. In the cosmos, the stage itself is part of the story. The expanding fabric of space. The most common way to explain this is with a balloon. Imagine you take a deflated balloon and draw dots on its surface. These dots are galaxies. Now, as you inflate the balloon, the rubber stretches, and all the dots move away from each other. A few things become clear. First, no single dot is the center. From the view of any one dot, all the others are moving away. This is exactly what we see in the cosmos. Second, the dots are not moving across the rubber. They are being carried apart by the rubber. This is the difference between an object moving through space and being carried along by the flow of expanding space. And finally, the apparent speed of separation depends on distance. Two dots close together move apart slowly. Two dots on opposite sides of the balloon move away from each other much faster, because there is more stretching rubber between them. This is what Hubble's law describes. The farther away a galaxy is, the faster it appears to be moving away from us. Now, imagine we are a tiny observer living on one of those dots. We shine a beam of light toward a distant dot. As the light begins its journey across the rubber, the balloon is still inflating. The light particle moves at its top speed relative to the rubber it is on, but its destination is being carried farther away by the expansion. It is like trying to walk up an escalator that is moving down and also stretching as you climb. This is what happened to the light from the most distant things we can see. That light began its journey to us nearly 13.8 billion years ago. When it started, the universe was much smaller, and the galaxy that sent the light was much closer to the location that would one day become ours. But during the 13.8 billion years the light was traveling, the space between its origin and its destination continued to grow. This brings us to a quiet but important distinction: the difference between light travel distance and comoving distance. The light travel distance is simple. It is how long the light has been traveling, which is about 13.8 billion light-years for the oldest light we see. But the asterisk comoving distance is the true distance to that object today, accounting for all the expansion that has happened. It is a cosmic yardstick that expands with the universe. When we measure the comoving distance to the source of that ancient light, the answer is not 13.8 billion light-years. It is about 46.5 billion light-years. That is the radius of our observable universe. Doubling it gives you the diameter, roughly 93 billion light-years. So, the light we see today traveled a path of 13.8 billion light-years through a space that was stretching. The starting point of that journey has been carried so far away from us that it is now, at this moment, 46.5 billion light-years away. The universe did not lie. The ruler just stretched while the measurement was being taken. Echoes of the beginning. This might sound like a convenient way to resolve a puzzle. But this model of an expanding universe is supported by enormous amounts of evidence. Chief among them is a faint glow that fills the entire sky, the cosmic microwave background, or CMB. The CMB is often called the afterglow of the Big Bang. For the first 380,000 years, the universe was an incredibly hot, dense fog of charged particles and light. The light was constantly scattering off electrons, unable to travel in a straight line. Then, at about 380,000 years, the universe cooled enough for electrons to combine with protons, forming neutral atoms. Suddenly, the light was free. The fog lifted, and the universe became transparent. The CMB is the light from that exact moment, a snapshot of the universe when it was just 380,000 years old. At the time, this light would have been a brilliant, yellowish-white glow. But in the 13.8 billion years since, as space has expanded, the wavelength of this ancient light has been stretched. This is called cosmological redshift. The light has been redshifted all the way into the microwave part of the spectrum, with a temperature of just 2.725 degrees above absolute zero. This faint microwave hiss comes from every direction in the sky with almost perfect uniformity. It is the cooled remnant of the Big Bang, and it provides solid evidence for the expansion model. We are seeing light that has traveled for nearly 13.8 billion years. By studying its properties, we can calculate how much the universe has expanded since that light was released. And that calculation tells us that the source of that radiation is now approximately 46.5 billion light-years away. But there is more. The CMB is not perfectly uniform. It has tiny temperature variations, just 1 part in 100,000. These were the seeds of all cosmic structure. And imprinted on these ripples is a pattern, baryon acoustic oscillations, or BAO. In the early universe, there was a cosmic tug-of-war between gravity pulling matter in and radiation pressure pushing it out. This created sound waves that rippled through the cosmic fog. When the universe became transparent, these waves froze in place, leaving a faint imprint on the cosmos, a preferred distance between galaxies, about 500 million light-years in today's units. By measuring this standard ruler in the distribution of galaxies, astronomers can map the expansion history of the universe. The results from BAO surveys align perfectly with the CMB data. They both confirm that the size of the observable universe is, indeed, 93 billion light-years in diameter. The story is confirmed by the echoes of ancient sound, a deepening mystery. So, space is expanding. But this raises a deeper question. Why? What is causing the expansion? For a long time, cosmologists thought it was simply leftover momentum from the Big Bang, and that the expansion was gradually slowing down due to the mutual gravity of all the matter in the universe. The answer came in 1998, and it was a quiet shock. Two teams of astronomers were using a specific type of supernova to measure cosmic distances. They found that very distant supernovae were fainter than expected. This meant they were even farther away than they should have been if the expansion was slowing down. The only way to explain this was if the expansion of the universe was not slowing down. It was accelerating. Something was gently pushing the universe apart, overcoming gravity on the largest scales. Scientists did not know what it was, so they gave it a name that reflects our uncertainty: dark energy. And it is not a small part of the story. Our best measurements suggest dark energy makes up about 68% of the universe. Dark matter accounts for about 27%. All the normal matter, every star and planet we can see, makes up just 5%. We live in a universe dominated by things we do not understand. What is dark energy? The honest answer is, we don't know. The leading idea is that it is a property of space itself, an intrinsic energy of the vacuum. This was an idea Albert Einstein once had, which he called the cosmological constant. He later called it his biggest blunder, but he may have been right for the wrong reasons. If empty space has its own energy, then as space expands, more of this energy is created, pushing space-time apart at an ever-increasing rate. This has profound implications. Early in the universe's history, gravity was dominant, and the expansion was slowing. But about 5 billion years ago, the density of matter dropped below the density of dark energy. At that point, dark energy took over, and the expansion began to speed up. We are living in the era of dark energy. This quiet, mysterious force is the engine driving the ongoing stretching of space. The awe-inspiring truth. So, is the universe lying about its size? No, it is telling a profound and subtle truth. It is our own intuition, shaped by a life where space is fixed, that is being deceived. We imagine a static stage, but the stage itself is stretching, growing, and carrying everything with it. The light from the farthest galaxies has been traveling for 13.8 billion years. But in that time, the space it was moving through has expanded so much that its starting point is now an almost unimaginable 46.5 billion light-years away. There is no paradox, no broken law. There is only the quiet, counterintuitive reality of an expanding spacetime. This leaves us with a humbling picture of our place in the cosmos. The accelerating expansion means there are galaxies whose light will never reach us. They have been carried beyond our cosmic horizon, their light struggling against a widening gulf of space it can never cross. We are forever separated from vast regions of our own universe. What we call the observable universe, that 93 billion light-year sphere, is just our bubble of reality. Every other galaxy has its own observable universe, centered on itself. Beyond our bubble, the universe likely stretches on, perhaps forever, filled with countless more galaxies that we can never know. We are left with a quiet truth. The universe is not just bigger than we think. In a very real sense, it is bigger than we can ever hope to see. The cosmic story is not a lie to be debunked, but a revelation to be embraced. It points toward a deeper, more complex, and far more wondrous reality than we might have imagined, inviting us to keep questioning, keep exploring, and keep looking up at the vast, stretching canvas of the night sky. If this quiet journey into the scale of the cosmos has offered you a new perspective, consider subscribing to the channel. There are still great mysteries to explore. What lies beyond the observable universe? What is dark energy? Let us know in the comments what cosmic question you find yourself returning to. And until then, keep looking up. Why we were wrong about the number of galaxies. For a long time, our view of the cosmos seemed settled. The number of galaxies in the universe felt enormous, almost beyond comprehension, but it was a number we could hold onto. Somewhere between 100 and 200 billion. It appeared in textbooks, documentaries, and in our own sense of cosmic scale. But that number, our map of the universe for decades, was incomplete. Not just slightly incomplete. What if it represented only a fraction of the truth? The quiet reality is that our universe contains at least 2 trillion galaxies, and even that number is likely just a beginning. This is the story of where those other galaxies were hiding, and what their discovery reveals about our place in the cosmos. It is a journey into the 90% of the universe we were simply not able to see. To understand this new reality, we must first return to a time when our vision of the cosmos was much smaller. For a generation, the estimate for the number of galaxies hovered around 100 to 200 billion. This figure was not a guess. It was the product of one of the most remarkable instruments ever built, the Hubble Space Telescope. Launched in 1990, Hubble offered a view of the cosmos free from the blurring effects of Earth's atmosphere. It could hold its gaze on a single point for days, even weeks, collecting the faint, ancient light from the edge of the visible universe. In 1995, astronomers pointed Hubble to a patch of sky that appeared, to all other telescopes, completely empty. The area was tiny, like a grain of sand held at arm's length. For more than 10 days, Hubble's eye stayed open, gathering every photon that arrived from this small window into the dark. The result was an image that changed our perspective, the Hubble Deep Field. Where there was once only blackness, the photograph revealed more than 3,000 distinct points of light. Almost everyone was not a star, but an entire galaxy. It was a humbling revelation. The universe was not just populated, it was overflowing. The work then became one of careful calculation. Assuming this small patch of sky was representative of the whole, astronomers multiplied what they saw across the entire celestial sphere. This led to an estimate of around 125 billion galaxies. Over the next decades, the experiment was repeated with more advanced instruments, producing the ultra-deep and extreme deep fields. Each time, more and fainter galaxies emerged. The official estimate settled into a range of 100 to 200 billion. For a long time, this was our map of the cosmos. It was a number large enough to feel infinite, yet contained enough to feel known. This number, of course, applied only to the observable universe. The universe is about 13.8 billion years old, so light from objects farther than that has not yet had time to reach us. But as that light travels, space itself expands. Because of this expansion, the most distant objects we can see are now much farther away, about 46.5 billion light-years. This creates a sphere around us, 93 billion light-years in diameter. This is our observable universe. The 200 billion galaxy figure was our census of everything inside this bubble. It was the accepted reality. And yet, it was only a small part of the story. The 200 billion galaxy estimate was a monumental achievement, but even as it became familiar, quiet inconsistencies began to appear. The orderly cosmos Hubble had shown us held puzzles that were hard to ignore. The first cracks in this reality came from two places: the limits of our technology and the predictions of our theories. First were the limitations of Hubble itself. It is a magnificent instrument, but it sees the universe primarily in visible and ultraviolet light, much like our own eyes. This creates a problem when looking for the most distant galaxies. Because the universe is expanding, light from these faraway objects gets stretched during its journey. This is known as redshift. Light that began as blue or ultraviolet is stretched into red and, eventually, infrared light. The very first galaxies to form are so extremely redshifted that their light reaches us almost entirely as infrared. Hubble's detectors could only catch the very edge of this light. It was like trying to listen to a symphony, but being able to hear only the highest notes. The deep, foundational sounds from the earliest cosmic times were simply inaudible. This blindness was made more significant by a theoretical paradox. While observational astronomers were counting galaxies, theoretical astrophysicists were running simulations to model how galaxies should form. These models, based on our understanding of gravity and dark matter, consistently predicted a universe filled with small, faint galaxies, far more than we could see. According to these bottom-up models, the universe did not begin with giants like the Milky Way. It began with countless small clumps of matter that slowly, over billions of years, merged to build the larger galaxies we see today. For every large galaxy, there should be dozens, or even hundreds, of smaller satellite galaxies orbiting it, the leftover material from this construction. But when we looked, we found far fewer than predicted. This became known as the dwarf galaxy problem. The discrepancy was significant. There were two possibilities. Either our leading theory of galaxy formation was wrong, or vast numbers of galaxies were out there that we simply could not see. They were too small, too faint, and too diffuse for even Hubble to resolve against the darkness. The stage was set for a quiet mystery. On one hand, an observational count gave us a tidy number. On the other, a compelling theory told us the universe should be much more crowded. The census was incomplete, but no one knew by how much. The resolution to this mystery came not from a single moment, but from a patient, 15-year effort to reconcile what we could see with what our theories predicted. The work was published in 2016 in a study led by astrophysicist Christopher Consolis. It did not just revise the old number, it revealed a universe more populous than had ever been imagined. The team's approach was to account for the galaxies that were too faint and too far away to be detected directly. Their work was a form of cosmic archaeology, piecing together the history of the universe's galaxy population to infer what was missing from our view. They began with the deepest images of the sky from Hubble and other telescopes, and converted them into 3 dimensions. The third dimension was time. By measuring each galaxy's redshift, they could determine its distance and look back to different epochs in the universe's history. This allowed them to create a series of cosmic maps, showing the density of galaxies at different points in time. What they found was quietly astonishing. As they looked further back in time, toward the early universe, the number of galaxies in any given volume of space increased dramatically. When the universe was just a few billion years old, there were about 10 times more galaxies per unit volume than there are today. This provided the first clear, observational evidence for the bottom-up theory of galaxy formation. The early universe was not a quiet place. It was a chaotic, swarming metropolis of countless small, faint galaxies. Over eons, these smaller systems merged and consolidated, their stars and gas building the larger, more massive galaxies that dominate the modern cosmos. The total number of individual galaxies, therefore, had actually gone down over time. With this insight, the team could perform their calculation. They created a mathematical model describing this rate of merging. By applying it to their maps of the early universe, they could calculate how many of those initial, faint galaxies must have existed to produce the number of larger galaxies we see today. The result of this calculation was the revelation. The observable universe must contain, at a minimum, 2 trillion galaxies. 2 trillion. That is 2 trillion. It was not a small adjustment. It was 10 times larger than the previous estimate. The study concluded that our census, based on what even our best telescopes could count, had only ever seen about 10% of the total galactic population. A staggering 90% had been hiding in plain sight, their light too faint and too redshifted for our instruments to register. This discovery also offered a new perspective on an old question, Olber's paradox. If the universe is infinite and filled with stars, why is the night sky dark? The 2016 study implied that, in principle, every point in the sky does contain part of a galaxy. The universe is completely wallpapered with them. We don't see a blazing white sky because the vast majority of these galaxies are invisible to us. Their light is stretched by cosmic expansion, absorbed by gas and dust, and is simply too faint to be seen. The universe we thought we knew, a vast ocean with 200 billion islands, was revealed to be something far grander. The 2016 study told us that 90% of the universe's galaxies were waiting in the darkness. But this was still an inference, a statistical argument. What was needed was direct proof, to actually see these phantom galaxies. For that, a new kind of eye was required, one designed to capture the faint, infrared glow of the universe's dawn. This was the purpose of the James Webb Space Telescope. Launched in 2021, JWST is 100 times more powerful than Hubble, and is tuned specifically to the infrared wavelengths where the early universe is revealed. It is a time machine, capable of looking back over 13.5 billion years to witness the birth of the first stars and galaxies. It has begun to turn statistical ghosts into faint, ancient light. JWST is not necessarily increasing the total estimate yet. Instead, it is providing the crucial evidence that the 2016 model was correct. In every deep field image it takes, JWST reveals a staggering population of faint, red, ancient galaxies. Surveys like the JWST Advanced Deep Extragalactic Survey, or JADES, have found hundreds of galaxies that existed when the universe was less than 650 million years old, an era where Hubble could only spot a handful. These observations confirm that the early universe was teeming with the small, dwarf galaxies that the models predicted. In fact, in some areas, JWST is finding 10 times more of these early galaxies than even optimistic predictions had suggested. This flood of new data is giving us an unprecedentedly clear picture of how galaxies evolve. We can now see the seeds of today's massive structures. We are witnessing the cosmic assembly of that early era, where galaxies were not isolated islands but active participants in a frantic process of merging. This direct evidence powerfully supports the bottom-up model that underpins the 2 trillion galaxy estimate. The reason that number is so high is because the universe started with a vast number of small parts that were later assembled into the larger structures we see today. In essence, if the 2016 study inferred the presence of these galaxies, JWST is allowing us to see them. It is showing us that the universe is not only as crowded as the team predicted, but perhaps even more so. Every image it returns is a quiet reminder that what we see in visible light is merely the tip of a colossal cosmic iceberg. The 2 trillion galaxy figure is no longer just a theoretical extrapolation. It is a baseline, a floor for the true census of the cosmos. The ghosts are finally coming into focus. Living in a universe with 2 trillion galaxies is more than a numerical update. It reshapes our understanding of the cosmos and our place within it. Consider the scale. Even if most of these 2 trillion galaxies are small, the total number of stars in the observable universe rises to a quietly staggering number. Something on the order of 2 sextillion, a 2 followed by 21 zeros. The universe is not just vast, it is unfathomably crowded. Our own cosmic neighborhood, with its 100 or so known galaxies, is now understood to be a far more typical arrangement than we once thought. This new census has also cemented our understanding of how galaxies grow. The bottom-up model of formation is no longer just a leading theory, it is an observed reality. We now know with much greater certainty that the universe began with a flurry of small structures that spent 13 billion years merging and growing. The Milky Way is the product of countless such events. We are living in a structure built from the remains of hundreds, perhaps thousands, of smaller galaxies consumed over eons. Our galaxy is not an island, it is a continent built from countless smaller lands. Perhaps the most profound implication of this discovery lies in the search for life. We can imagine a grander version of the Drake equation, one for the entire observable universe. Its first variable is the number of galaxies. By increasing that number from 200 billion to 2 trillion, we have expanded the potential stage for life by a factor of 10. The number of potentially habitable planets skyrockets into the trillions or quadrillions. Even if life is an exceptionally rare event, a universe with 2 trillion galaxies provides so many opportunities that the odds become more compelling. It does not prove anything. It only stretches the canvas of possibility to a breathtaking new size. Finally, this discovery is a powerful lesson in scientific humility. It reminds us that our knowledge is always provisional, limited by our technology. For decades, we were confident in a number that turned out to be only 10% of the truth. It makes one wonder, what else are we missing? Even with JWST, we are only seeing the brightest of those early galaxies. How many more lie just beneath its threshold of detection? The 2 trillion number is a floor, not a ceiling. The story of science is one of receding horizons. Each time we build a better instrument, the universe reveals itself to be grander and more complex than we knew. We thought we had counted the islands, only to realize we were standing on the shore of a continent, with an entire world left to explore. We began this journey with a familiar number, 200 billion galaxies, a figure born from the eye of the Hubble Space Telescope. We followed the story through the quiet puzzles that hinted at a deeper truth. We witnessed the patient work that led to the 2016 revelation, a moment when our universe expanded tenfold to a minimum of 2 trillion galaxies. And now, we see the James Webb Space Telescope delivering the tangible proof, turning statistical inference into visible, ancient light. The ultimate takeaway is a profound one. The universe is vastly more crowded and complex in its structure than we imagined. The 90% of the cosmos that was hidden from us was not empty. It was filled with the faint, primordial building blocks of everything we see today. The next time you look up at the night sky, Remember what lies hidden in the darkness. Do not just imagine a few 100 billion other galaxies. Imagine a sea of 2 trillion. Imagine the unfathomable number of stars, planets, and possibilities contained within them. We live in an age where the very scale of our reality is being rewritten. The universe has never felt larger, and the quest to understand it has never been more meaningful. If this quiet exploration of the cosmos helps you unwind, consider liking the video and subscribing to the channel. And let us know in the comments below what parts of this new cosmic picture feel the most significant to you. The universe is a lie and we can prove it. There is a story we are told about where we are. It begins with the ground beneath our feet and the sky above our heads. It expands outward to the idea that we are here, in a universe that is solid, predictable, and real. From our earliest years, we learn that the universe is everything. The sum total of all existence, born around 13.8 billion years ago in a single, fiery moment. But what if that story, our most fundamental truth, isn't the whole story? What if the foundation itself is not quite what it seems? Imagine looking up into the night sky. You see the familiar stars, distant galaxies, a canvas of cosmic history. Now, imagine that everything you see, everything astronomers have ever seen, and everything we could ever hope to see, is a limited perspective. Not a deception, but a beautiful and intricate misunderstanding that has shaped our view of reality since we first looked up. This is a journey into how our entire, 93 billion light-year wide universe might be little more than a single bubble in a quiet cosmic ocean. An ocean filled with other realities, other bubbles, each a universe of its own, forever separate from ours. This isn't philosophy. It's an exploration to the edge of modern cosmology, guided by the same mathematics that describes our own world. By the end of this, you will see how the Big Bang might not have been the beginning, but simply our beginning. And the clues have been hiding in plain sight. The comfortable story, defining our universe. Before we look beyond the story, let's first get comfortable with the one we know. What is the universe? For most of human history, it was the stars we could see with the naked eye. Then, telescopes revealed that some of those faint smudges of light were entire galaxies, each holding billions of stars. Today, thanks to instruments like the Hubble and James Webb telescopes, we understand our place with a quiet precision. We live on a planet, orbiting a star, in a galaxy called the Milky Way. Our galaxy is just one of perhaps 6 trillion galaxies within what we call the observable universe. When we talk about the size of the universe, this is what we mean. It is a sphere of space with us at the center, stretching about 46.5 billion light-years in every direction. This gives it a diameter of 93 billion light-years. That number is so large it's difficult for our minds to hold. An analogy might help. If our entire Milky Way galaxy were the size of a single grain of sand, the observable universe would be a concrete sphere more than 600 feet across. It's a staggering volume, filled with more stars than there are grains of sand on all the beaches and in all the deserts on Earth. The story we are told is that this immense stage was born about 13.8 billion years ago in the Big Bang. From a point of incredible density and heat, everything we see erupted into being. But a question arises here. If the universe is only 13.8 billion years old, how can it be 93 billion light-years across? Shouldn't the farthest light have only had 13.8 billion years to travel? This is the first hint that reality is a little stranger than it appears. The answer is that space itself has been expanding. It's not that galaxies are flying away from us through space, it's that the fabric of space-time between us and them is stretching. A common analogy is a loaf of raisin bread rising in an oven. The raisins don't move through the dough. The dough itself expands, carrying them apart. 2 raisins far from each other will separate faster than 2 that are close together, simply because there is more dough expanding between them. So, the light from the most distant galaxies we see today left its source long ago. But in the 13.8 billion years it took that light to reach our telescopes, the space it was crossing was continuously stretching. That initial distance has expanded into the 46.5 billion light-year distance we measure today. This is our cosmic home, a 93 billion light-year sphere, containing trillions of galaxies, all originating from a single event. It's a neat, awe-inspiring picture. It is also, as we are about to see, just the part of the story we're able to read. The rest of the book begins to reveal itself when you ask a simple question. What happens at the edge? The edge of everything. When you hear, edge of the universe, you might picture a physical wall, a final boundary. But the reality is more subtle, and in a way, more profound. There is no wall. There is no hard stop. The edge of our observable universe is not an edge of space, but an edge of time. The farthest thing we can see is a faint, uniform glow called the cosmic microwave background, or CMB. This isn't light from a star. It is the afterglow of the Big Bang itself. It was released about 380,000 years after the beginning, when the universe cooled enough for the first atoms to form, allowing light to travel freely for the first time. This ancient light, stretched and cooled by 13.8 billion years of expansion, is the earliest snapshot of our universe. It represents the boundary of our vision. Any light from before that time is hidden from us, blocked by the hot, dense plasma of the early cosmos. This creates a horizon of visibility, much like the horizon on the ocean. You know there is more ocean beyond what you can see, but the curve of the Earth limits your view. In the same way, we have good reason to believe there is more universe beyond the CMB. Light from those more distant regions simply hasn't had enough time to reach us. With each passing moment, our horizon expands. In theory, we should slowly see more and more of the universe as time goes on. But here, reality introduces another complication. A cosmic current that seems to be locking away the vast majority of existence forever. That current is called dark energy. In the late 1990s, astronomers found something unexpected. The expansion of the universe is not slowing down, it's accelerating. Something is gently but persistently pushing space-time apart, working against gravity. We don't know what it is, so we give it a quiet name, dark energy. It appears to make up about 68% of the universe, and its effects are profound. Because of this accelerating expansion, galaxies beyond a certain distance are receding from us faster than the speed of light. This doesn't break any laws of physics. The galaxies themselves aren't moving through space that fast, the space between us and them is stretching that quickly. But the consequence is the same. The light from those galaxies is like a person trying to walk up an escalator that is moving down faster than they can climb. That light will never reach us. This creates a second, more permanent boundary, the cosmic event horizon. It marks a point of no return. Any galaxy that crosses it is lost to us forever. We are becoming more and more isolated in our own cosmic neighborhood. In the very distant future, as this process continues, galaxies will seem to fade from our sky one by one, until only the Milky Way and its closest companions remain in a vast, dark quiet. This is where the scale of our limited perspective truly comes into focus. The universe isn't just the 93 billion light-year bubble we can see. That bubble is simply our home, a place defined by the speed of light and the age of the cosmos. Outside its walls lies a potentially vast expanse of space and galaxies that we are, in a fundamental way, unable to ever see. But what is out there? Is it just more of the same? More stars, more galaxies, stretching on and on? Or is it something else? To explore that question, we have to go back to the beginning, and the moments just before it, where a subtle inconsistency in our story opens up a view of reality so vast it makes our entire universe feel like a single grain of sand on an endless shore. The quiet inconsistency, the inflation problem. The Big Bang theory is one of the great successes of modern science. It correctly describes the expansion of the universe, the existence of the cosmic microwave background, and the amount of light elements like hydrogen and helium. It is the bedrock of cosmology. And yet, by the 1970s, it became clear that this bedrock had some quiet, unanswered questions. Questions so fundamental they suggested our picture of the very beginning was incomplete. The first was called the flatness problem. According to Einstein's theories, mass and energy curve spacetime. The universe can have one of three shapes: closed, like a sphere; open, like a saddle; or flat, like a sheet of paper. For decades, our best measurements have shown the universe to be incredibly, almost perfectly, flat. The problem is that a flat universe is a state of remarkable balance. It requires a very specific amount of matter and energy, known as the critical density. If the early universe had just a tiny fraction more, gravity would have pulled everything back together in a big crunch. If it had a tiny fraction less, the expansion would have been too fast for gravity to form galaxies or stars. For the universe to be this flat today, its initial density had to be fine-tuned to an accuracy of 1 part in 10 to the power of 15. That's like balancing a pencil on its point and having it stay upright for 13.8 billion years. It's not impossible, but it feels like a profound coincidence. The second, even deeper puzzle was the horizon problem. As we've discussed, the cosmic microwave background has an incredibly uniform temperature everywhere we look. The sky in one direction is 2.725 Kelvin, and the sky in the opposite direction is the same, to an accuracy of 1 part in 100,000. This even temperature suggests that these regions were once in contact, able to exchange energy and smooth out any differences, like two ends of a metal bar held over a flame. But in the standard Big Bang model, these two opposite points in the sky were already vastly separated when the CMB was released. They were never in causal contact. Light, the fastest thing there is, wouldn't have had enough time to travel between them to even out their temperatures. So why are they identical? It's like finding two people on opposite sides of the Earth who have never met, yet somehow share a perfectly synchronized history. These quiet problems were serious. Then, in 1980, a young physicist named Alan Guth proposed a new idea. An idea that would not only resolve these questions but also change our understanding of the universe's first moments. He called it cosmic inflation. Guth suggested that in the very first fraction of a second, from roughly 10 to the power of minus 36 to 10 to the power of minus 32 seconds after the Big Bang, the universe went through a period of unbelievably rapid, exponential expansion. Driven by a hypothetical energy field, space didn't just expand, it swelled. A region of space smaller than a proton was blown up to the size of a grapefruit almost instantly. Then, just as suddenly, this period ended. Its energy was converted into the hot soup of particles and radiation that we associate with the familiar Big Bang. Inflation, in this sense, was the bang in the Big Bang. This single idea addressed the problems beautifully. It solved the flatness problem because such an immense stretching would flatten any initial curvature, just as inflating a tiny, wrinkled balloon to the size of the Earth would make any patch on its surface appear perfectly flat. And it solved the horizon problem. The entire observable universe we see today was once a single, infinitesimally small, connected region before inflation started. All its parts were in contact with each other before they were flung apart, which preserved their uniform temperature across the vastness of space. Inflation was a triumph. Its predictions have been confirmed by observations with remarkable accuracy. But as physicists like Andrei Linde and Alexander Vilenkin explored the idea further, they realized their theory had another, even more profound implication. One that would demote our entire universe and hint at the true nature of reality. We are at the edge of a quiet paradigm shift. The theory that so perfectly explains our own origins seems to point toward something infinitely grander. If this calm exploration into the cosmos helps you think or unwind, consider subscribing to the channel. What you've heard so far is just the setup. The real story is about to unfold, as we pull back the curtain on the cosmos itself. The emerging truth: eternal inflation and the cosmic ocean. Inflation was a monumental success. It saved the Big Bang model and made predictions that proved to be true. But as physicists looked closer at how inflation might work, they found an almost unavoidable consequence. Andre Linde, along with Alexander Vilenkin, realized that inflation, once started, might be impossible to stop everywhere at once. To understand this, we can return to the inflating field, the engine of that early expansion. You can picture this field as a ball rolling down a landscape of hills and valleys. When the ball is high on a plateau, the field has a lot of energy, and this energy causes space to expand exponentially. This is inflation. When the ball rolls into a valley, its energy is converted into matter and radiation, and a hot Big Bang begins. Here is the crucial insight. In the world of quantum mechanics, the field doesn't behave like a single, smooth ball. It's probabilistic. Due to quantum fluctuations, in some regions of space, the field will roll down the hill, ending inflation. But in other regions, a quantum fluctuation can push the ball back up the hill, keeping that patch of space in its inflationary state. The regions where inflation continues expand exponentially, while the regions where it stops, like our universe, expand much more slowly. This means that even as pocket universes are forming, the inflating space between them is growing so stupendously fast that it will always dominate the total volume. This process, once it starts, may never truly end. It could be eternal. Think of it like a pot of gently boiling water. The eternally inflating spacetime is the pot of water. Every so often, a bubble forms. That bubble is a universe, like ours, where inflation has ended and a hot Big Bang occurs. The bubble expands, cools, and forms galaxies and stars. But outside that bubble, the rest of the water is still simmering, constantly creating more space and spawning new bubbles. These bubbles are carried apart by the rapid expansion of the space between them, so they can never touch or interact. This is the theory of eternal inflation. It suggests our Big Bang was not the beginning. It was just the moment our local bubble formed from a much larger, eternally inflating, multiverse. Our entire universe is just one bubble in a quiet, cosmic foam of other bubble universes, each born from its own Big Bang. The eternally inflating parent space is the larger reality. It is the cosmic ocean. Our universe is just one droplet. New universes might be forming right now, far beyond our cosmic horizon, where we could never hope to see them. This, here, is the revelation. The very theory we need to explain our own universe's basic properties, its flatness and uniformity, leads logically to the conclusion that our universe is probably not all there is. Inflation suggests eternal inflation, and eternal inflation suggests a multiverse. The universe, as one single entity, may be a story that is only part of a much larger narrative. The truth could be a multiverse, a vast, self-reproducing cosmos that has been going on for an unimaginably long time. We are not the center of existence. We are not the main event. We are a footnote, a small, isolated pocket of order in an endless, quiet storm of creation. And the implications of that realization change how we see everything. Life in the bubbles, infinite worlds, infinite possibilities. Once you consider the premise of eternal inflation, the consequences cascade into some of the most profound ideas in all of science. It changes our understanding of our own existence and our place in the cosmos. The first implication is that other universes could have different laws of physics. That landscape the inflating field rolls down? In some theories, like string theory, it isn't just one hill and valley. It's a cosmic landscape, with a vast number of different valleys, perhaps as many as 10 to the power of 500. When a bubble universe forms, the inflated field settles into one of these valleys at random. Each valley could represent a universe with its own unique set of rules. The speed of light, the strength of gravity, the charge of an electron, all of these could be different from one bubble to the next. Most of these universes would likely be sterile. A slight change in the strong nuclear force, and stars couldn't form. A slight change in the cosmological constant, and a universe might collapse instantly or fly apart too fast for anything to gather. The vast majority of bubbles would be cosmic failures, brief flashes of existence, or empty, desolate voids. But in a potentially infinite multiverse, vast majority means little. If you have an infinite number of chances, every possible outcome can eventually happen. And this provides a simple, if unsettling, perspective on one of the great mysteries in physics, the fine-tuning problem. Our universe appears exquisitely fine-tuned for life. The constants of nature seem to have just the right values to allow for stars, planets, and us. For decades, some have seen this as evidence of design. But the multiverse offers another view, the anthropic principle. It's not that the universe was designed for us. It's that we could only find ourselves in a universe with properties that allow us to exist. We live in one of the rare bubbles where the physics came out just right. It's like waking up on a planet with liquid water and a breathable atmosphere and asking, why is this planet so perfect for me? The answer is because you wouldn't be there to ask the question on any of the trillions of other planets that aren't. Our existence is not a miracle, it's a selection effect. We won a cosmic lottery. The implications become stranger still. If the multiverse is truly infinite, and there are a finite number of ways particles can be arranged in any given space, then the universe must repeat. Not just similar universes, but exact duplicates. Somewhere out there, in a bubble so far away we can never reach it, there may be another Earth, with another version of you. And another, where you made a different choice this morning. And another, where dinosaurs still roam. In an infinite multiverse, anything that can happen, will happen. In fact, it will happen an infinite number of times. Your life may not be unique. You may be one iteration in an infinite set, spread across an endless ocean of disconnected realities. This is the ultimate conclusion of eternal inflation. It is the ultimate demotion, from the center of the universe to just one of an infinite number of copies of ourselves. The faintest clues, hunting for cosmic bruises. This is all a fascinating story. Infinite worlds, different physics. But is it science? A scientific theory should be testable. Can we ever hope to find evidence for these other universes? The answer, incredibly, is maybe. While we can never travel to another bubble, we might be able to see faint traces of ancient encounters. If another bubble universe formed close to ours in the early moments of the multiverse, it's possible they could have collided. Such a collision would have left an imprint, a bruise, on our sky. This bruise might appear as a specific pattern in the cosmic microwave background, a large, circular spot that is either slightly hotter or colder than the background around it. And here is where the story becomes quietly exciting. There is an unexplained feature in our CMB maps known as the cold spot. It's an unusually large, cool patch of sky that our standard models have difficulty explaining. One leading idea is that it's caused by a massive, supervoid, in that direction, a region with far fewer galaxies than average. But some studies suggest the voids found so far can't fully account for the spot's temperature. This has left the door open for more speculative ideas. And one of the most tantalizing is that the cold spot could be a cosmic bruise, the first faint hint of a collision between our universe and another. Now, this is a highly speculative idea. The evidence is far from conclusive, and there may be other, much simpler explanations. It could just be a statistical fluke. But for the first time, the question, do other universes exist? Has moved from philosophy into the realm of observational science. We are no longer just guessing. We are learning how to look. We began this journey with a simple picture of our reality, a single universe, born in a Big Bang. We saw how quiet inconsistencies in that picture, the flatness and horizon problems, led to a radical new theory of the universe's first moments, cosmic inflation. And we saw how that same theory, when followed to its logical conclusion, seems to replace our simple picture with something infinitely more complex and magnificent. A reality where our Big Bang was not the beginning, but just a beginning. Where our universe is not the whole of existence, but a single bubble in an eternally simmering cosmic ocean. The 93 billion light-year sphere we call home is a lie of perspective. It is our cosmic horizon, the limit of what we can see, but not necessarily the limit of what is. Beyond that edge, pulled away from us by the quiet expansion of space, lies an unseeable expanse that inflation suggests is vastly larger than our own observable bubble, and potentially infinite. And within it, new universes may be born at every moment. What does this mean for us? It means we are perhaps simultaneously less significant and more precious than we ever imagined. Less significant, because we are a tiny part of a reality that may be infinite in time and space. But more precious, because we find ourselves in one of the rare bubbles where the laws of nature allow for complexity, consciousness, and wonder. We are a way for the universe to know itself. Even if our universe is just one note in an infinite cosmic symphony, the fact that we are here to hear the music at all, to question its source, and to piece together the story of our own existence, that may be the most incredible truth of all. The universe as we know it might be a limited story, but it's a story that has given birth to listeners. And the search for the rest of the symphony has only just begun. How large is the observable universe really? We exist on a small world of rock and water, circling an ordinary star in a quiet arm of a vast galaxy. And for as long as we have been aware of the sky, we have looked into its depths and asked fundamental questions. How far does it go? And where, if anywhere, does it end? For a time, we have found an answer in a number. A figure so large it seems to define the scale of our cosmic home. We have measured the sphere of everything we can possibly see, the observable universe, and found it to be 93 billion light-years across. It is a distance that resists comprehension, a scale that feels like a form of eternity. It represents, for us, a kind of ultimate boundary, the edge of our known reality. But this number, like all measurements in science, is not an ending. It is the beginning of a deeper and more complex story. It is a story of cosmic horizons we can never cross, of galaxies that are quietly vanishing from our future, and of a universe whose ultimate fate has been thrown into question. The true nature of our cosmic home is not just about its immense size, but about how that size is changing, and what that change implies for our distant future. To understand this, we must first take a journey to the edge of what we can see, to understand what that 93 billion light-year number truly means. Deconstructing the cosmos. What is 93 billion light-years? To approach the question of the universe's size, we must begin with its fundamental unit of distance, the light-year. It is not a measure of time, but of distance. Light is the fastest thing in the cosmos, traveling at 300,000 kilometers every second. A light year is the distance it covers in a single year, about 9.5 trillion kilometers. To place that in perspective, the light from our own sun takes just over 8 minutes to reach Earth. The next nearest star, Proxima Centauri, is about 4.2 light-years away. Our own Milky Way galaxy is roughly 100,000 light-years from edge to edge. When we look out into space, we are looking into the past. The light from the Andromeda galaxy, our nearest large galactic neighbor, began its journey 2.5 million years ago. We are seeing it not as it is, but as it was. This is the key to understanding the observable universe. Astronomers have measured the age of the universe, largely by studying the faint afterglow of the Big Bang, and found it to be approximately 13.8 billion years old. A simple guess, then, might be that the universe is 13.8 billion light-years in radius. After all, light has only had that much time to travel. But this intuition misses a crucial element of the story: the expansion of space itself. The universe is not a static container. Space itself is dynamic, it stretches. The common analogy is of dots drawn on the surface of a balloon. As the balloon inflates, the dots move apart not because they are traveling across the surface, but because the surface itself is expanding, carrying them along with it. A photon of light traveling between two galaxies is crossing a stretch of space that is itself growing. It is making progress, but the distance it must cover is constantly increasing. This is why the observable universe is so much larger than 13.8 billion light-years. When we see the light from the most distant galaxy, that light has been traveling for nearly the entire age of the universe. But during its long journey, the galaxy that emitted it has been carried much farther away by the expansion of space. When physicists account for this expansion over cosmic history, they find that a galaxy whose ancient light is only now reaching us is currently located about 46.5 billion light-years away. Since we can see this distance in every direction, this defines a sphere with a diameter of 93 billion light-years. This number itself is not fixed, it is refined as our measurements improve. In 2013, data from the Planck satellite gave us a more precise calculation of the universe's expansion history. This adjustment slightly changed our estimate for the size of the observable universe. This wasn't because the universe physically changed, but because our understanding became more exact, a common story in science. Hallucigenia did not change, our understanding of hallucigenia did. The cosmos, too, waits patiently for our understanding to catch up. So, 93 billion light-years is the current best estimate for the edge of everything whose past we can see. It is a shell of ancient light surrounding us. But this boundary, the edge of what we see now, is not the only horizon that matters. There is another, and it holds the secret to our changing cosmic home. Two horizons and a disappearing act. The idea of a shrinking cosmic home seems to contradict what we have just established. If space is expanding, shouldn't our view of the universe grow larger over time, as more distant light finally reaches us? To untangle this, we need to introduce two different cosmic horizons. They define two very different things: our past and our future. The first is the asterisk particle horizon. This is the boundary we have been discussing, the edge of the observable universe right now. It is our cosmic rearview mirror, the maximum distance from which light emitted in the past has had time to reach us. Because time moves forward, this horizon does expand. Tomorrow, light that has traveled for 13.8 billion years and one day will arrive, and our particle horizon will be marginally farther away. In this sense, the volume of space we can see does grow. But there is a second, more consequential horizon: the asterisk cosmic event horizon. This horizon is not about the past, it is about the future. It marks a point of no return, a boundary beyond which any event that happens now asterisk will never be seen by us, no matter how long we wait. The reason for this is a force known as dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down under the pull of gravity, as had been expected. It is accelerating. Some quiet, repulsive property of space itself is pushing everything apart at an ever-increasing rate. Because of this acceleration, there is a certain distance from us where the fabric of space-time is stretching faster than the speed of light. Nothing is moving through space faster than light, which would violate relativity. Instead, space itself is expanding at a superluminal rate, carrying distant galaxies along with it. A galaxy that crosses this threshold is, for all practical purposes, gone from our future. Any light it emits from that moment on is like a swimmer trying to move against a current that is faster than they can swim. The light will be swept away from us, its journey never to be completed. This is the cosmic event horizon. Its distance is a matter of ongoing calculation, but the principle is what matters. And this is the source of the quiet disappearing act. As the accelerating expansion continues, galaxies that are currently inside our event horizon are being pushed toward it. Over billions of years, one by one, they will cross that threshold. Their light will redshift into oblivion, fading until it is undetectable. What this means is that the number of galaxies we can ever hope to see or interact with is finite, and it is decreasing. The observable universe, defined by the particle horizon, will continue to grow in volume. But the asterisk contents of that universe, the number of galaxies we can actually witness, will plummet. Imagine being on a ship in the middle of a vast, calm ocean. Your horizon is the farthest you can see. But there is a powerful, invisible current pulling every other ship away from you. Slowly, you watch as they slip over the edge of your view, one by one, disappearing forever. Your view of the ocean remains, but it becomes emptier. Eventually, you are left alone. This is the predicted fate of our cosmos under the standard model of constant dark energy. Trillions of years from now, our sky will be almost entirely dark. Every galaxy outside our own small, gravitationally bound local group will have been pushed over the event horizon. Future astronomers would have no evidence that other galaxies ever existed. The sprawling cosmos we see today will have vanished, leaving behind an immense and quiet void. Our cosmic home, in terms of what we can witness, is shrinking. But what if the force driving this disappearance isn't what we think it is? What if the story of a lonely, expanding future is not the only possibility? A change in the constant. For nearly 3 decades, the story of the universe's fate seemed settled. The discovery of accelerating expansion led to our standard model of cosmology, in which dark energy is a cosmological constant, an unchanging property of space. This constant energy would drive the universe to expand forever, leading to a big freeze, or heat death. It was a settled, if somber, conclusion. But science is a process of constant questioning. In recent years, data from major cosmological surveys has returned subtle hints that dark energy might not be constant. It might be evolving. The evidence comes from projects like the Dark Energy Spectroscopic Instrument, (DESI). It is a monumental undertaking, equipped with 5,000 robotic fiber optic eyes that can measure the light from thousands of individual galaxies at once. Over its mission, it is building the largest 3D map of the universe ever created. By charting the positions of galaxies at different times in cosmic history, these surveys can reconstruct how the expansion rate has changed with unprecedented precision. They do this by measuring a faint pattern in how galaxies cluster, an echo of sound waves from the early universe known as baryon acoustic oscillations. This pattern serves as a kind of standard ruler. By measuring its apparent size at different cosmic distances, scientists can map the expansion history of the universe. And what these maps are beginning to show is a subtle deviation from the standard model. The data, when combined with other cosmological observations, suggests a universe where dark energy may have been stronger in the past and has been weakening over the last few billion years. The statistical significance of this finding is still below the threshold required for a definitive discovery, and scientists are rightly being cautious. Yet the fact that independent surveys are pointing toward the same question has the field listening closely. If dark energy is dynamic, it would imply something other than a simple property of space is at play. Physicists have a hypothetical name for this kind of changing dark energy: quintessence. Unlike a constant, quintessence is envisioned as a new type of energy field that permeates space, its density changing over time. Depending on how it changes, it could cause the expansion of the universe to speed up or, possibly, slow down. The idea of quintessence opens up a new realm of possibilities for the universe's future. The lonely, quiet expansion of the Big Freeze is no longer the only option. If the force of dark energy can weaken over time, the long-running contest between the outward push of dark energy and the inward pull of gravity could have a very different outcome. The balance of power could shift. And if that happens, the fate of our universe is not an endless expansion into darkness, but something else entirely. Two competing narratives. For a quarter century, the Big Freeze was the accepted destiny of our universe. But if the new hints in the data hold up, if dark energy is indeed weakening, we must confront a radically different possibility. A future where the expansion of space reverses. A future known as the Big Crunch. This is not just speculation. Theoretical physicists have developed models that explore what might happen if dark energy continues to weaken and eventually changes from a repulsive force to an attractive one. In such a scenario, the cosmic expansion that has defined our universe for 13.8 billion years would slow, halt, and then reverse. The universe would begin to contract. The Big Crunch would be the Big Bang played in reverse. Instead of galaxies rushing away, they would rush toward each other. The sky, once destined to become dark, would instead grow brighter. As the universe shrank, the temperature of the background radiation would rise from its current frigid state to thousands, then millions of degrees. Space itself would contract, squeezing everything together. In the final moments, the very fabric of reality would unravel as the entire universe, all of space, time, and existence, collapsed into an infinitely hot, infinitely dense singularity, just like the one from which it was born. We now stand at a genuine crossroads in our understanding. We have two competing narratives for our ultimate fate. Scenario 1. The Big Freeze. Dark energy is constant. The acceleration is permanent. Galaxies will continue to disappear over our event horizon, leaving us in an increasingly isolated, dark, and cold universe that will expand forever. Scenario 2. The Big Crunch. Dark energy is dynamic and weakening. The acceleration is temporary. In the far future, gravity may regain control, pulling the universe back together in a final, fiery collapse that will end time and space as we know it. The difference could not be more dramatic. One is an eternity of quiet emptiness, the other is a finite life followed by a return to the beginning. And the most incredible part of this story is that we are living in the moment when we might finally learn which path the universe is on. So, how large is the observable universe? We began with a number, 93 billion light-years. But the true answer is a dynamic and evolving story. It is a story of two horizons. The particle horizon defines the 93 billion light-year sphere of our past, showing us ancient light from the dawn of time. But the event horizon, the boundary of our future, tells a more chilling tale of a shrinking, cosmic home, where most galaxies are destined to vanish from our sky. And just as we were coming to terms with this lonely fate, a new chapter has opened. The force responsible for this isolation, dark energy, may not be constant. Evidence from our most advanced instruments is hinting that it may be weakening, challenging the long-accepted ending of a Big Freeze with the alternative of a Big Crunch. We are living in an unprecedented era of discovery. A new generation of observatories, the Vera C. Rubin Observatory, the Euclid Telescope, and the Nancy Grace Roman Space Telescope, will map the cosmos with unparalleled detail. These instruments, working in concert, will help us solve the mystery of dark energy. They will tell us if it is constant or if it is changing. They will tell us if we are destined for an infinite, cold darkness, or a finite, fiery return. The journey to understand the size of our universe has led us to the ultimate question of its destiny. It is a reminder that in cosmology, every answer reveals a deeper question. We may feel small in the face of these immense scales, but it is our ability to ask these questions, to build these incredible instruments, and to piece together the story of the cosmos, that gives our existence meaning. We are the universe's way of knowing itself. And right now, we are on the verge of uncovering one of its greatest secrets. The universe is lying to you. There is a number you may have heard. 93 billion light-years. It is offered as the size of the universe, a piece of information to be held and memorized. But this number is not quite what it seems. It is not a deliberate falsehood, not a malicious deception, but a quiet misunderstanding, born from the way our minds try to make sense of a reality they were not built to contain. The true story of the universe's size is not a simple fact. It is a paradox, one that begins to unfold the moment you realize that space itself is not what you think it is. And understanding that paradox can change the way you see everything. The misunderstanding is a simple one. We imagine the universe as a vast, unchanging room, and the galaxies as motes of dust drifting within it. But the truth is more dynamic and more strange. The room itself is growing. The very stage of existence is stretching, carrying everything along with it. The universe is not just expanding, it is an expansion. In that small shift of language, a secret of the cosmos is held, and the key to understanding why its true scale feels so impossible to grasp. This is the story of that secret, and of the journey to the final frontier, our own perception. The paradox of a number. Let us begin with the number itself. 93 billion light-years. It appears in articles and documentaries, a familiar piece of cosmic trivia. But to pause and consider it is to find a problem. The universe, we are told, is 13.8 billion years old. This age is found by looking at the oldest light in the cosmos, the faint glow left over from the Big Bang, called the cosmic microwave background. Our minds, shaped by a lifetime on a very small planet, perform a natural calculation. If 13.8 billion years have passed, then the farthest we should be able to see is 13.8 billion light-years away. Light from anything more distant has not had time to reach us. The universe, then, should be a sphere with a diameter of roughly 27.6 billion light-years. The number is still enormous, but it feels logical. The real number is 93 billion. This is not just a larger figure, it is a paradox. How can the universe be wider than the time it has had to exist? How could anything have traveled a distance that seems to require moving faster than light, the fundamental speed limit of the cosmos? This is the first clue that the universe does not follow the rules of our everyday intuition. It is the loose thread that, when pulled, begins to unravel our entire idea of space. To resolve this, we must think not of objects moving through space, but of space itself as an active, dynamic thing. Imagine a single photon of light, sent on its way from a distant galaxy shortly after the Big Bang. For 13.8 billion years it travels at the speed of light. But while it travels, the very fabric of space it moves through is also stretching. It is like trying to walk up an escalator that is moving down. You move forward at your own speed, but the surface beneath you carries you backward, adding to the journey. That ancient photon had to cross a cosmic-scale escalator. The space it was moving through was expanding, creating more distance as it went. And so, the galaxy that released that photon, once much closer, is now about 46.5 billion light-years away from us. Double that for the diameter of our vision, and you arrive at the seemingly impossible figure of 93 billion light-years. This is the observable universe, the sphere around us from which light has had time to arrive. It is not an edge but a horizon, the boundary of our perception. Beyond it, the universe almost certainly continues, perhaps for an immensity we cannot calculate, or perhaps forever. And here, the misunderstanding becomes personal. The universe is not lying. Our own minds are. They evolved to navigate the distances of a savanna, to judge the path to water or the approach of a predator. They are masters of the immediate, the tangible, the human scale. But they are not equipped for the cosmic. We are trying to understand an exponential reality with a linear mind. And that is a recipe for a quiet and beautiful confusion. The journey of discovery. Our journey to understanding this began not in space, but in the early 20th century, with astronomers looking through telescopes at faint, fuzzy patches of light they called nebulae, from the Latin for cloud. For a long time, it was believed these were clouds of gas inside our own Milky Way galaxy. The universe was our galaxy. And that was all. But some were not so sure. One was an American astronomer named Vesto Slipher. In the 1910s, he analyzed the light from these nebulae, spreading it into a spectrum of colors. Within that spectrum, he saw the chemical fingerprints of their elements. But he noticed something strange. For most of the nebulae, those fingerprints were shifted toward the red end of the spectrum. This is known as redshift, a cosmic version of the Doppler effect. Just as a siren's pitch lowers as it moves away, light from a receding object stretches, shifting toward red. Slipher found that almost all the nebulae were moving away from us at incredible speeds. The universe was not static. But the meaning of this was not yet clear. The astronomer who would unlock it was Edwin Hubble. At the Mount Wilson Observatory in the 1920s, using the most powerful telescope of its time, he looked at the Andromeda Nebula to settle the debate. Was it a cloud inside our galaxy, or something else entirely? His breakthrough came from finding a special star within it, a Cepheid variable. As astronomer Henrietta Swan Leavitt had discovered, these stars pulsate at a rate directly tied to their true brightness. They are a standard candle. By measuring a Cepheid's pulse, you can know how bright it truly is. By comparing that to how dim it appears, you can calculate its distance. When Hubble did this, the result was staggering. Andromeda was nearly 1,000,000 light-years away, far outside the Milky Way. In an instant, the known universe expanded 100-fold. Those nebulae were not clouds. They were other galaxies, island universes, scattered through a vast cosmic ocean. Hubble then remembered Slipher's work. He and his assistant, Milton Humason, began measuring the distances to many galaxies and their redshifts. A clear pattern emerged. The farther away a galaxy was, the faster it was moving away from us. This relationship, now called Hubble's law, was the definitive proof that the universe is expanding. It pointed to a history, a time when everything was closer together. It was the first observational evidence for what would become known as the Big Bang. To understand what Hubble found, there is a simple analogy: a loaf of rising raisin bread. As the dough bakes, it expands, and all the raisins move farther apart. From the perspective of any single raisin, all the others appear to be moving away. The farthest raisins move away the fastest, because there is more expanding dough between them. This is what Hubble saw. The expansion is happening everywhere at once. Crucially, the raisins are not moving through the dough. They are being carried by the expansion of the dough itself. In the same way, galaxies are not flying through space like shrapnel. The space between them is what is expanding. This dismantles our intuitive view of the universe as a container. There is no empty void the universe is expanding into. It is creating more space as it goes. This also changes our picture of the Big Bang. It was not an explosion in space, it was the explosion of space. It did not happen at one point. It happened everywhere. In the beginning, the entire observable universe was in an incredibly hot, dense state. From that moment, space itself began to expand, cool, and thin out. Asking what came before the Big Bang or what is outside the universe may be questions that do not make sense, because both before and outside require time and space to exist. The journey from Slipher's first hints to Hubble's law was a process of letting the universe tell us how it works, rather than forcing it into the familiar shapes of our limited experience. We are about to explore how this cosmic expansion rewires our very sense of reality, and why the human mind is built to struggle with it. It is a quiet, mind-bending journey. If this kind of calm exploration of the cosmos is something you enjoy, consider subscribing to the channel. We explore these kinds of questions often, and you may not want to miss what is next. The revelation. So, we are left with a universe that is 13.8 billion years old, yet 93 billion light-years across, because spacetime itself is expanding. This brings us to the most personal part of the journey, the revelation. The lie is not in the numbers. It is in our perception. The greatest barrier to understanding the universe is not in our telescopes, but in our own minds. Let us revisit the observable universe. It is a sphere with us at the center. Its edge, the cosmic horizon, is the point from which light has had just enough time to reach us. Every observer in every galaxy has their own observable universe. It is a bubble of perception, not a physical wall. What lies beyond it? Our best theories suggest it simply continues, much the same as it is here. Some studies suggest the entire universe, if it is finite, is at least 250 times larger than what we can see. It may even be infinite. Our entire cosmic reality could be a single grain of sand on an endless beach. This is where our minds begin to fail. Psychologists sometimes call this magnitude estimation failure. We evolved to estimate the distance to the next hill, not the next galaxy supercluster. Our mental tools are based on linear experience. Past a certain point, the difference between a million, a billion, and a trillion becomes conceptually vague. They are all filed away in a mental folder labeled, a very large number. A million seconds is about 11.5 days. A billion seconds is nearly 32 years. A trillion seconds is almost 32,000 years. Our minds can feel the difference between a 2-week holiday and a lifetime, but struggle to distinguish the numbers in the abstract. Let us try to build a ladder of scale, knowing it will break under its own weight. Start with Earth. Its diameter is about 12,742 kilometers. Now, to the Sun, 150 million kilometers away. A commercial jet would take over 17 years to fly there. We call this distance 1 astronomical unit. Go further. The Voyager 1 spacecraft is the most distant human-made object. After nearly half a century, it is 24 billion kilometers away, just beginning to leave our Sun's protective bubble. To reach the nearest star, Proxima Centauri, would take Voyager 1 about 75,000 years. Zoom out again. Our Milky Way galaxy is about 100,000 light-years across and holds hundreds of billions of stars. If our solar system were the size of a quarter, the Milky Way would be the size of North America. Let that settle for a moment. The nearest major galaxy, Andromeda, is 2.5 million light-years away. When the light we see tonight began its journey, modern humans did not exist. Our galaxy and Andromeda belong to the Local Group, a collection of about 50 galaxies. This group sits on the edge of the Virgo supercluster, with thousands of galaxies. And even that is just one lobe of a grander structure, the Laniakea supercluster, home to 100,000 galaxies stretching over 520 million light-years. We are still nowhere near the edge of our observable universe. Each step on this ladder is a leap our minds can follow mathematically, but can no longer feel. The distance becomes an abstraction. This is the heart of the lie. The universe is not a static thing with a size we can comprehend. It is a process, an expansion, and its scale is a matter of time and perception as much as distance. Due to the accelerating expansion of the universe, driven by what we call dark energy, most of the galaxies we can see are already beyond our reach forever. They have been carried away by the stretching of space so fast that even if we left today at the speed of light, we could never arrive. The space between us and them is expanding faster than we could cross it. We are in our own local cosmic neighborhood, able to see a vast universe we can never touch. The lie of the universe, then, is the lie of simplicity. We want a single, neat number. The universe refuses. It offers instead a paradox. A finite age but a size that exceeds it, a visible horizon that is not an edge, and galaxies we can see but can never visit. The revelation is that understanding the universe is not about memorizing numbers. It is about recalibrating our intuition and accepting that the rules of reality on a cosmic scale are different. Space is not a void. Time is not absolute. They are interwoven parts of a single, expanding fabric. The universe is challenging you to let go of terrestrial common sense and embrace a new, cosmic one. We began with a number, 93 billion light years, and found it to be a quiet paradox. We journeyed back to the first discoveries that our universe was not a static stage, but a dynamic, expanding cosmos, carried on the current of space itself. And finally, we turned inward, to our own perception, and found that the greatest hurdle is the mind we used to see. A mind evolved for a small world, now tasked with conceptualizing infinities. The universe feels impossibly vast because our intuition makes it so. The truth is more subtle and more beautiful. The universe is not a container, it is the thing contained. Space is not a backdrop, it is an actor. Its expansion is the growth of reality itself. The next time you look at the night sky, remember the misunderstanding. Remember that your mind wants to see a simple picture. But you know the truth. You are not a tiny object in a vast, fixed space. You are part of a dynamic, unfolding process. You are a momentary consciousness born from 13.8 billion years of cosmic expansion, living inside a bubble of perception, looking out at a universe that is constantly becoming more than it was. The universe isn't lying to you. It's telling you a story. A story of scale, of time, and of the beautiful, humbling limits of human understanding. And the most incredible part is that you are here to listen. If this journey into the paradox of the cosmos sparked your curiosity, please consider subscribing and joining our community of explorers. There are endless quiet mysteries to unravel, and we are just getting started. Feel free to share your thoughts in the comments below. What aspect of the universe's scale do you find the most difficult to hold in your mind? Thank you for watching.